So good afternoon. If you can take your seats, because we have to restart the program. You know, is quite full. So we resume our afternoon session, and I call Corino Cegrai to chair the first speaker of afternoon session. Please, Corino.
No, you should wait for applauding Laura later. So first of all, welcome back to the afternoon session, and it's a great pleasure and honor to introduce the next speaker, Professor Laura De Marco from Harvard University. So I'll say a few words about Laura. Mini biography. So she's American, even though I discovered she has Italian grandparents, from which the Italian name that you pronounce Laura. So she got her PhD thesis in 2002 at Harvard under the supervision of Fields medalist Kurt McMullen. And she spent, after that, almost 20 years in Chicago. And actually, she moved through institutions, from Dixon instructor at University of Chicago. Then she was for several years at the UIC, University of Illinois of Chicago, where she became full professor, and then at Northwestern University. And since 2020, she is back in her alma mater at Harvard, as the official title is Radcliffe Alumni Professor at Harvard Radcliffe Institute and Professor of Mathematics at Harvard Faculty of Arts and Sciences. And the research of Laura De Marco is really the crossroad between several areas of research. So in particular, between complex dynamics, which in itself is between dynamical systems and complex analysis, and arithmetic geometry, which has connection to number theory and algebraic geometry. And she's also one of the seminal figures and founders of the area of research of arithmetic dynamics, of which maybe she will tell us about a bit today. And her work was recognized by several awards. In particular, she was an invited speaker at the 2018 ICM, the previous International Congress of Mathematics. And she was the fellow of the American Math Society, the inaugural class, and since 2020, also a member of the National Academy of Science. And she received several prizes, including the Sutter Prize of the American Math Society, and very recently, the Alexanderson Award from the American Institute of Mathematics for work with Holly Krieger and Hexie. And today, she will tell us about rigidity and uniformity in algebraic dynamics. So let's welcome Laura De Marco. Yeah.
Thank you. Thank you very much for that introduction. And to the organizers also, thanks so much for this opportunity to speak here on this very special occasion and in this very special venue. I'm awed. Wait. Okay. So my goal today is to tell you a bit about some very recent and, to me, very exciting developments in what I've called here algebraic dynamics, but more broadly, really the connections between dynamical systems, as Corino mentioned, and number theory and algebraic geometry. I've spent myself the last 10 or even 15 years thinking about various connections between these subjects, especially, well, on one hand, how we can use tools from number theory and algebra to address questions about certain dynamical systems, but also in the other direction, which is somewhat more surprising and more recent, to be able to use some of the dynamical methods, the theory of stability and bifurcations from dynamical systems, and apply them to some algebraic questions to get some answers of interest to arithmetic geometers. So I won't be able to tell you the whole story today. I'll just hopefully give you one little snapshot of what's happening in this area. But first, let me say a word about what what I mean by these subjects. So I've tried to summarize the entire subject in one short slide here. On one hand, so the type of dynamical systems that I'm interested in are those, well, discrete time systems, so defined by just a map from a space X to itself. Time passing just means iterating this mapping repeatedly. But I'm interested in complex and algebraic dynamical systems, so I'm going to assume that X has the structure of some algebraic variety. It has algebraic or complex structure, and of course then I want the map to be a morphism. I want it to respect that structure. I'll give some examples in a moment. At the level of points, the most basic thing we're interested in is the orbit of a point. In other words, the sequence of points where you start with some point in your space and you apply f to it repeatedly and you get a sequence, and you want to understand what that sequence might look like. And I should say, at its really most basic level, one of the things we're interested in are the orbits of minimal complexity, the smallest orbits. And that might mean the finite orbits. So which orbits, for example, are periodic, start at x and return to x after finitely many steps, or pre-periodic just means eventually cycling. We might ask, how many periodic points do we have? How are they distributed within the space? What's the geometry, the configuration of the collection of periodic orbits? It's a very basic question that one can ask about a dynamical system. On the other hand, to just try to create a parallel here, in arithmetic geometry, one of the things we're interested in is, well, in some sense, the same object, maybe even the same space. But now I'm thinking of my algebraic variety here as defined over a field which is not algebraically closed. So maybe the field is the field of rational numbers, or a finite extension, a number field, or a finite field, or a function field, so a field of rational functions. And now remember, these algebraic varieties are defined by polynomial equations, and these are just the sets of solutions to some collection of polynomial equations. And so we're interested in the solutions, which might themselves live in the original field. So that's what x of k denotes, the set of solutions, the set of points in your variety, which are defined over the given field. Now we also have a notion of simple or simplest in this setting. And I won't give a definition, but here I had periodic, which were sort of the simplest orbits. Here we might have a notion of complexity, for example, the notion of height as introduced by Weil in the 1930s. So one might ask, in general, where are the points of low height, of low complexity? And we can also ask, how are they distributed within your variety? Of course, to make sense of that, we might wish to pass to an algebraic closure of the field in order to have lots of them. So these are just some basic questions. As I said, I'll give an example in a moment. But as I said, my goal is really to create the parallel, to draw the relation between the dynamics on one side, the algebra on the other, with somehow the geometry of x in between. And I wrote height functions at the bottom because height function is really, at least in the arithmetic setting, height functions are the tools that we've been using to draw to create this link. All right, so here's an example. I guess I didn't write any formulas, but I will in a moment. So the simplest complex algebraic variety, one might argue, is the Riemann sphere. And so x here is the projective line over the complex numbers. Now we know from complex analysis class exactly what the morphisms are. These are just the rational functions of one complex variable. And if we view them as dynamical systems, although the formulas are simple, the dynamics are very, very complicated, as you may have seen. So this illustration here is just one example. I don't remember the exact formula offhand, but it happens to be a function of degree 2, again, of just one variable. And what I've plotted here is supposed to be an illustration of what's called the Julia set. I'm sure you've seen lots of pictures of Julia sets before. Here, the yellow points under iteration are converging to a particular attracting cycle of period 7. The pink point converging under iteration to another attracting cycle of period 7. This happens to be an illustration for an example that has a symmetry. And the Julia set is the boundary between the yellow and the pink, where the chaotic dynamics takes place. That's just one example or one picture. But for my story relating to the algebra, I want to emphasize a very special class of these examples. There's a particular collection of rational functions that comes from studying elliptic curves, the geometry and the algebra of elliptic curves. So here, one more slide ahead. There's no dynamics yet, there we go. So if we take an elliptic curve, which geometrically is just a torus with a distinguished point, because remember it's a group, and you take any endomorphism of this group, so it's a morphism on the underlying curve here, but also respects the group structure, it will commute with, so this is the inverse for the group operation, and so it descends, the quotient by that degree 2 identification here is just the sphere, and it will descend to a morphism of the sphere. So you get an interesting class of examples, it turns out, from looking at these endomorphisms of elliptic curves. And one might hope to use the dynamics to address questions, the many, many questions that have been asked over hundreds of years about arithmetic of elliptic curves. I should say from a dynamical point of view, these are maybe the Julia set of this example. You wouldn't see a very pretty fractal picture like you do on the previous slide. The Julia set is the entire sphere, because in this example, these endomorphisms are just linear in appropriate coordinates. They're expanding everywhere. The periodic points are dense. They're all repelling. They're relatively easy to understand from a dynamical point of view. So that's not why I want to study them. But I want to study them for actually maybe a more basic reason. So this is really the example I wanted to give you right at the beginning. So I mentioned on the earlier slide a notion of low complexity for a dynamical reason, meaning, say, finite orbit or periodic. And from an arithmetic point of view or an algebraic point of view, there was a height notion of low complexity that I mentioned but did not define. In this setting, they coincide, at least when we can define the height. So let's just take a simple example. If you take the endomorphism, which is multiplication by 2 on your elliptic curve, so in other words, you take a point and you add it to itself. So this defines a morphism here of your favorite elliptic curve, whichever one you want, and it will always descend to give you a rational function. In this case, it will be a rational function of degree 4, because this one here will have topological degree 4 also. So just low complexity on the algebraic side would correspond to torsion points. So for the group, I've just reminded you the definition of torsion on the slide. For the group, it just means add the point to itself repeatedly, and you get to the 0. Remember that a point is pre-periodic if under iteration for a dynamical system, it eventually cycles. So it has a finite orbit. And so it happens in this case, and it's a very, very elementary argument, you can write it down in a few lines, that a point here will be torsion for any your favorite endomorphism here, well, as long as it's not an automorphism, if and only if the corresponding downstairs point has finite orbit. So in particular, we could study the algebraic structure, the group structure, the torsion structure of the elliptic curve by looking dynamically. That's all I want to emphasize. One can use dynamics to try to study something about the algebra or the group structure of the elliptic curve. And you can do this for, the whole family of elliptic curves. There are lots of them. And if it happens to be defined over a number field, or over the field of rational numbers, for example, then you can also start using the arithmetic notion of height. For example, what's called the Néron-Tate height that we use to study elliptic curves or abelian varieties in higher dimensions, defined over number fields. There are corresponding heights defined over other finitely generated fields, and you can still study this correspondence, but then you have an additional equivalence related to the height that I did not write down. Okay. Oh, I forgot, I did have a remark on this slide. So just to mention, I've only mentioned this one-dimensional example, and I only gave you the example of rational functions of the Riemann sphere as a morphism. This story can be carried out or exists in higher dimensions too. If you take, say, an abelian variety, so a higher dimensional torus, which is also algebraic, is projective, you can take an endomorphism of that abelian variety. You cannot do the same thing. There won't necessarily exist this nice quotient on some nice smooth space here, but you can embed the abelian variety into some larger projective space and extend the morphism to some larger projective space, at least this one. So this, say, multiplication by 2 endomorphism extends to a morphism of a higher dimensional projective space, and you can try to play the same game and study the algebra via the dynamics. So in a somewhat tongue-in-cheek fashion, I've just mentioned the theory of abelian varieties can be embedded into the theory of algebraic dynamical systems on PN. We certainly can't answer all the questions that have been answered about abelian varieties by studying them dynamically, but some questions we can, and that's what I'm hoping to talk about. Okay, so as I said, I want to mention, I said, some very recent developments, well, in algebraic or arithmetic dynamics, but more generally in geometry, in arithmetic and complex geometry. So I want to mention 2 examples of these recent developments. I'm not stating any theorems on this slide. I'm just going to state the themes, because I want to get to a more dynamical statement. But I'll just mention, in the context of what are called the Manin-Mumford conjecture and the Mordell-Weil, well, theorem, and Mordell conjecture, all of these are theorems now, but uniform versions of them. So let me just mention what they're about without making any precise statements. The Manin-Mumford conjecture was about compact Riemann surfaces, or complex algebraic curves, as they're embedded in their Jacobians. The Jacobian is an abelian variety. It's a torus. And in particular, it has a group structure. And this is supposed to be my picture here of some 2-dimensional abelian variety with say, a genus 2 curve embedded into it. The torsion points of these abelian varieties are dense. In the complex topology, the usual topology, they're a dense set. But the question at the time was, well, we have this nearly canonical embedding of this curve sitting inside this torus. How does it interact with the group structure? In particular, how does it intersect the torsion points of this group? And it was proved in the 1980s that for any of these what are called Abel-Jacobi embeddings, there's only finitely many torsion points on that curve. I'm going to assume the curve is at least genus 2. So there are only finitely many torsion points on this curve. Now that was proved in the 80s, and there was an original proof, and there have been many people revisiting that theorem, that proof, other proofs. But I want to mention some recent work, which was in the direction of controlling uniformly how many points can this curve intersect. And I mean uniform over all curves of, say, a given genus. So let's say you have all curves of genus 2. This is some 3 complex dimensional family of curves, up to isomorphism, that is. And so then you have this large family of curves. They're moving around inside their Jacobians. Is it possible that there's a uniform bound on that number of torsion points? And that's what I mean here by uniform. And I say recent developments. In 2021, so last year, this is a preprint year, not a publication year. So this was just announced last year. Lars Kuhne has managed to provide a proof that indeed there is a uniform bound on the number of torsion points that can lie on a curve within its Jacobian, independent of your choice of embedding. The uniform bound depends only on the genus. We know that as the genus grows, the curves can be embedded in a more complicated way, and you can get more and more torsion points. But there is a bound depending only on the genus. And what's really special about this, I just want to emphasize, what's really special about this is it's all curves over the field of complex numbers. In the past, and I've not mentioned many of the people thinking about this, but for example, in the recent work of Katz, Rabinoff, and Zurich Brown, they were studying the same question, but their bounds were field dependent. What field, what extension of Q are you working with? And then you could give a bound with some additional arithmetic conditions, additional hypotheses. I mentioned some of my own work here just briefly because we were also working over C, so it was sort of a first effort to get a field-independent result, but we were only working in genus 2, and Kuehne managed to give a complete argument. And using techniques from arithmetic geometry, I should mention, all of these proofs, in fact, are arithmetic, including the original Raynaud's, even though the end result is for curves over the field of complex numbers. And then another thing I want to mention, again, the same Kuehne appears here, except among other authors. And again, these are preprints from last year, so just announced results. I'll just mention briefly. So Mordell-Weil and Mordell in the context of higher genus curves is about, now it's not over C, but again, over, say, a number field. So a finite extension of Q, and looking just on the curve itself and looking at those rational points on the curve. When the genus is bigger than 1, Faltings proved that there are only finitely many rational points on any curve defined over, say, a number field and of genus bigger than 1. But one could again ask the question, well, how many are there? And is there a uniform bound depending on something? And so these authors very recently have shown indeed there are uniform bounds in the family of all curves of a given genus, but it depends on a bit more, well, here it has to depend on the field in question. As soon as you pass to the algebraic closure, there will be infinitely many points on your curve. But there's an additional ingredient in their bounds, which I'll just mention, depends on, in fact, how the curve related to how it's embedded in its Jacobian, and something called it's an Abel-Jacobi rank associated to the curve. So there's some extra ingredients, but uniformity is the question, and uniformity is where we're headed, and there are really, I believe, some very exciting developments in this direction. I mentioned also genus 1, by the way, because the similar question could be asked. If you look at the set of rational points on an elliptic curve, then, well, it's been known since the 1920s, Mordell for working over the field of rational numbers themselves, Q, and Weil for number fields, which, by the way, is when he was introducing heights, which at the end of the day is a tool for all of these things, the height functions. They were studying the set of rational points on an elliptic curve and proved that forms a finitely generated subgroup. It's not finite for elliptic curves. And then Mazur and Morel gave uniform bounds to control that set of rational points in the genus 1 case. So there was uniformity known already in the genus 1 setting. Okay, so I have my watch, but hold on. 2:55, okay. All right, so because of what I mentioned earlier, how we can take a billion varieties and certain endomorphisms of a billion varieties and extend them to morphisms of an ambient projective space, one can in fact think of these questions that I've mentioned here, or this topic, as somehow a subset of a more general collection of questions about dynamical systems more broadly. So one could think of this type of question as really looking at, say, a morphism of some algebraic variety, and you fix some subvariety, and you're interested in how the low complexity points intersect your subvariety. In particular, say, the periodic or the pre-periodic points of your morphism. So one can ask very similar questions, and there have been some recent developments also on this side in more general contexts. This one I won't talk about at all. I just mentioned Nicole Looper is one of my former students, so I wanted to make sure I mentioned some of her work. Pieces of this story can also be extended to a more general dynamical context where we are interested in controlling the number of periodic or pre-periodic rational points when you're given a morphism that's defined over a number field. And so there's work in these directions. But, okay, again, I said I wasn't stating any precise results or any theorems on this slide, but I do want to mention a key ingredient in many of the proofs. I mentioned height functions just loosely. Really, one of the tools that's been used has been very fruitful for all of these questions and many of the actual proofs that I've cited are what's called arithmetic equidistribution theorems. And there's a good history of those as well, but all of them have a similar flavor. There's a notion of complexity of a point. So it could be a height, or it could be something else, but there's some notion of low complexity, and the points of minimal complexity or low complexity, the key idea, is that these will be somehow uniformly distributed with respect to a natural measure on your space. So if you're given a dynamical system, there's a canonically associated height function which will pick out the points of low complexity. The small height points will correspond to the periodic points. And then one can study, as these authors did, the distribution of those points. And this has turned out to be a very powerful tool. I should mention the distribution, the equidistribution here, does not just take place on the complex manifold. When you're working over, say, a number field, your manifold lives with a family of other analytic spaces working in, say, p-adic spaces for every prime associated to your number field. So you get really not just one manifold and one distribution, but an infinite collection of, I shouldn't call them manifolds, an infinite collection of analytic spaces and an infinite collection of associated distributions, and you get some kind of global equidistribution results that lead to a number of these finiteness type statements. And again, I want to emphasize the 2021s here are all referring to the preprint year, again, announced last year. There was a significant breakthrough, which is what led exactly to these proofs, a significant breakthrough in our understanding of arithmetic equidistribution and really what class of varieties we can work with, what types of morphisms were allowed, what types of height functions were allowed to work with on certain, I should say, really strictly speaking, I should say arithmetic varieties over Z, so over spec Z. So that's the setting for these results. And they're not just projective now, we can do it also in certain quasi-projective settings as well. And that was actually the breakthrough. Okay, but this slide was meant to be an overview. Oh, good, it's 3 o'clock. So in the rest of the talk, I want to specialize my discussion to what should be a very simple, hopefully simple, illustration of this big picture. And so I'm actually going to tell you a story that is really some of my own work from a little over 10 years ago, and how it's built up into some more recent results, and how we can really get a lot of leverage from these equidistribution results that were just proved, and where we're going from here. So I'll try to keep it as simple and as down to earth as I can now. So, as I said in the beginning, the simplest setting would be dynamics on the Riemann sphere, so dynamics on the projective line. So here, the most famous family of examples would be, say, the quadratic polynomials. You think of C as a parameter, C as a complex number, and I'm just looking at this particular family of quadratic polynomials, but viewed as dynamical systems. So I'm interested in the orbits of points. Of course, we saw this picture earlier in Martin Heier's talk. He showed us the Mandelbrot set. This is the family that gives rise to this famous fractal image. And just in case you're not aware, as many people are not, what is the actual definition of this set This is the set of all parameters C for which the orbit of 0 is bounded. So it has a very simple definition. The set of parameters for which the orbit of C 0 is bounded. And that gives rise to this beautiful and complicated object that we still do not fully understand. So although it's been studied actively since we were able to create pictures of it, which was in the, I guess the first pictures date to the late 1970s, but we didn't have good computer pictures until the 1980s, and people have been studying it since then, and there are still some very interesting and deep questions about the structure of this fractal. But that's not what I'm going to talk about. Let's go back to the notion of periodic and pre-periodic. So just again to remind you, a point is periodic if its orbit, if it comes back to itself under finitely many steps. Pre-periodic means it eventually cycles. So for these examples, if you fix just one example, so you fix your favorite C value, you have one of these polynomial dynamical systems, there will always be infinitely many points that are periodic or pre-periodic. So there are lots of them in the plane. You can think about it, they're just solutions to certain polynomial equations. So if I fix C, this is some polynomial in Z. If n is larger, some polynomial of degree 2 to the power n. So it should have 2 to the n solutions. Maybe some of them are multiple, but generally it'll have 2 to the n solutions. So there are lots and lots of them. And then you let n and m grow. Here's just what one of these polynomials would look like. Here's an example of degree 8 polynomial for that particular n and m. Okay, so there are lots of periodic points for each individual example. And these Julia set pictures illustrate where the periodic points are. So for example, if you take C equals 0, this is just the squaring dynamical system. This is a picture of the unit circle, this axis and the scale here. The periodic points are just, well, 0 is periodic, it's fixed. And then all of the roots of unity are pre-periodic. In fact, those are exactly the pre-periodic points for the squaring operation. So pre-periodic if and only if 0 or a root of unity. But for most other examples, we cannot describe the periodic points or pre-periodic points explicitly, so we like to draw the pictures, and as you've probably seen, the pictures get very complicated. Here are just a few examples for 3 more. I've drawn them all on the same scale. Well, I've drawn what's called the filled Julia set, which is just the set of points that have bounded orbit. It's a very easy algorithm. It's very quick to draw such pictures, as opposed to solving those polynomial equations and trying to plot the periodic points themselves. An important fact is that the periodic and pre-periodic points are dense in the boundaries of these filled Julia sets. So they're accumulating and living everywhere on this fractal curve boundaries. So to picture the periodic points, you can just draw the points with bounded orbit. Here are just a few more. Of course, they're not all connected. Here's an example where it's a Cantor set. Here's an example where it has no interior, but it's connected. Here are 3 more examples that are Cantor sets. Okay, Julia sets are really beautiful, and there's a lot to say about them. But going back to my question of, say, rigidity and uniformity in this context, one could ask the following. To what extent does the set of these periodic or pre-periodic points determine the polynomial? So if you know just the set of points that are periodic, do you know the polynomial? And I mean set, so forget the polynomial equation that it satisfies, forget the periods, forget the length of the orbit, just knowing that the point is periodic or pre-periodic. What can you say? Are those pictures the same for 2 different polynomials? Well, in this particular case, at least for this class of examples, no. It's a fundamental fact in this field that those pictures are only the same if the 2 polynomials are the same. That's really because they're monic polynomials. It's relatively fairly, one uses complex analysis to prove this, but it's not too hard. So in particular, the set of periodic or pre-periodic points, which determines the boundary of that, which determines what's called the Julia set, the boundary of that filled Julia set determines the polynomial for these examples. Okay, but one could then naturally ask, how many pre-periodic points would really determine the polynomial? How many pin it down uniquely? Can you have a family of examples that share the same 300 periodic points or pre-periodic points? How many common pre-periodic points can they have? So the two have in common. Okay, so one could ask this question. Although I should say it's not obviously even well formulated. How many suggests that it's a finite number. A priori, it could be that two different systems have infinitely many periodic points in common, even if they're different. Right? So they could overlap in some infinite set. I just want to show a couple pictures so you see that it's not completely obvious how to address this problem. So this was the picture I showed you earlier for c equals 0, just the squaring. So the periodic points and pre-periodic points are the roots of unity together with 0. And here's the picture for z squared minus 1, this particular fractal curve. All of the periodic and pre-periodic points accumulate or lie in the boundary of this shape. And here's their intersection, or their overlap. So the most obvious thing to do is to look at how the fractal curve for the minus 1 case intersects the non-fractal curve, which is the circle, for the other example. So one might just look at the intersection. If the intersection happens to be finite, well, then there's not a whole lot to say, or one could count the number of intersection points. But remember, these are fractal curves, and so of course, if you zoom in, you expect to see the same thing at all scales. And so while we definitely see some intersection here, if you zoom in, you realize that there are really a number of intersection points. This is the arc of the circle here, superimposed on top of the other fractal curve. And if you were to zoom in more, you would see a lot more intersections. And it's possible, I haven't done it, but it's possible if they continue to zoom and zoom and zoom, you might see more and more intersection. So as sets, from a topological point of view, the closure of the periodic and pre-periodic points, they can intersect a lot. They can certainly have infinite intersection in general. In this example, I don't know, I didn't check. Of course, for other examples, if you take just small perturbations, this is a fairly large perturbation because I wanted to emphasize that the difference, but if you take small perturbations of two different maps, their Julia sets might look similar, so you would expect lots of overlap. So it's actually quite hard to tell whether those intersections are going to be at the pre-periodic points or not, especially if it's infinite and complicated. Okay. All right, so this is just the first result in this direction that I had proved together with Matt Baker, who was trained as a number theorist, I should emphasize, and at that stage I had not done any work related to number theory at all. And but what we realized by combining the complex analytic methods that we'd been using to study these dynamical systems and the number theoretic methods, the p-adic analysis that he had been using and had been working on for some years, that we could get some version of a rigidity statement. This was proved, by the way, before I state the theorem, independently by Xinyi Yuan and Shouwu Zhang at the same time. I'm only stating this for this one-dimensional setting, polynomial dynamical systems from C to C. There's a version of this that holds much more generally. But what's the statement? The statement here is that if you look at the set of all pre-periodic points for F and the same for G, and you look at their intersection, you should expect the intersection to be finite. It's just a finiteness statement. Very much analogous to the Manin-Mumford type of statement that I mentioned earlier. And in fact, certain versions of this have overlap with the Manin-Mumford, the Raynaud theorem that I mentioned earlier. But the statement here is that either this intersection is finite or it's not, but there's a reason for it. So if it's infinite, then in fact the sets coincide. And F and G are basically the same dynamical system. So there's a dichotomy. Either F and G are essentially the same, or their overlap of pre-periodic points must be finite. Okay. So in particular, for the quadratic polynomial family that I mentioned, the z squared plus c, we know that this intersection will be finite as long as the two parameters are not the same. And I should emphasize this is really for all over C. These are really complex family. Although, as I said, the tools, we're using arithmetic tools. So just an example, so the same example that I showed you earlier, where we have the unit circle, and we have this fractal curve for z squared minus 1, it turns out for this example, well, it's easy to see that 0, 1, and minus 1 are pre-periodic for both examples. One can just compute their orbits. But remember, the others might lie in these intersections where the curves seem to have lots of overlap. How do you know if there are going to be any pre-periodic points there? Well, that's actually a rather simple, very elementary algebraic argument that shows that, well, the set of pre-periodic points, they're defined by polynomial equations. So this intersection is invariant under the Galois action, under all of the Galois conjugates of one of these common points. If you have one in here, all of the Galois conjugates must also lie in this set. But we know exactly what the Galois conjugates of a root of unity are. There are other roots of unity. And so we can say that if you had a point in here which was pre-periodic for both, then all of these other roots of unity, which have to be spread around on the circle, would have to be common pre-periodic points too. But they can't be, because they're going to infinity under iteration for this z squared minus 1 example. So one can use a very simple idea from algebra to show that these 3 points are actually the only common pre-periodic points. And the general proof of this theorem is somewhat similar, a little bit souped up, but somewhat similar. Let's see. So I have a sketch of the proof here, but I'm not going to read it. I just want to mention a couple things. The basic strategy of this proof and many proofs like it is to first assume that you're working with algebraic family, something that's defined over Q or over a number field. So we have this Galois action of Q bar over Q to work with. And in that setting, certain things become a little bit easier. And as I said, one of the key tools is a uniform distribution. So it turns out if this intersection were infinite, we know it's Galois invariant, then turns out it would have to be uniformly distributed. But with respect to what? With respect to a measure which is invariant for one of the maps, but also invariant for the other map, and that would force, it turns out, the maps to be the same in this example. And then, because this is really a statement about parameters in the complex numbers and not over Q bar, one has to be able to extend to C. And one of the ways that we did it, in fact, I should mention, there is some work to do. One of the key observations was how to pass to the complex numbers when these bounds are not uniform. A standard specialization argument didn't work, and so one of the things we did was work with certain equidistribution in those Berkovich analytic spaces that I mentioned earlier. And that was the strength of having this extra spaces to work with, because the equidistribution did not hold over C in that case. All right, so I don't want to say anything else about this. This was just a finiteness statement, though. So this is some kind of rigidity statement. The title of my talk was Rigidity and Uniformity in Complex or Algebraic Dynamics. It certainly does not answer this question. How many common pre-periodic points can you have for these types of systems? This really simple example, quadratic polynomials, z squared plus c. Is it possible to close the door? Because I'm hearing voices, and I don't know if it's from the, thank you. It's distracting. Thank you. So how many can you actually have? So if you're just handed two dynamical systems, we saw an intersection of 3 in my previous example. How big can it be? Well, who knows, but uniformity. So now, building on some of the more recent techniques using height theory and equidistribution, we were able to show in this special case that there is in fact a uniform bound, so that any pair of these polynomials have at most that many common pre-periodic points. So over the entire two-dimensional family of pairs, parameterized by C1 and C2, complex, there's some uniform bound on the number, on the size of this intersection set. And one of the key ingredients to do that, well, I mentioned that equidistribution, the uniform distribution of this set, if it's infinite, it has to be uniformly distributed with respect to some natural measures. Really, the idea was just to boost that up to get a quantitative form. In other words, how fast is the equidistribution? How, and more precisely, for the algebraic folks among you, really what that means is we need an estimate on sizes of, say, Galois orbits, or how many of these preperiodic points we have. And if you can control the size of the orbit, you can control how close a finite set of points is to the distributing, the limiting measure. So a quantitative version of these arithmetic equidistribution theorems is one of the key ingredients. I'll pause at this moment just to say, of course, many people ask me, well, what is M? How big is it? In fact, as I said, we saw an example with 3 common preperiodic points. How big can that get? I don't know. I should say that the proof is effective in the sense that you can chase through the entire argument and you can extract a number. And we did that. And fortunately, by Martin Heirer's definition, it's finite, but not very finite. So the best we could do, just chasing through our argument without making effort to optimize, we know that this number M is no bigger than a very big and ridiculous number. So from a practical point of view, this bound is totally useless. It's not going to help us compute anything. And so actually, I just wanted to mention the largest known in this particular family. So there's some interesting computational questions here I should mention, but the largest known in this particular family is for this particular pair, which happen to both be defined over the field of rational numbers, not even though I'm working over all the field of C. It turns out these rational ones appear to give the biggest intersection. Here, maybe the next slide shows their Julia sets separately. So for these 2 examples, these are pictures of their filled Julia sets, and this is the superposition of the 2. We know that there are at least 26 common preperiodic points, but this is the record holder. This is the most we know. Here's what they look like. You can just use a computer to find them for you, these 26. It's not too hard, but we don't know if that's all of them, nor do we know if there are any pairs that have more. My guess is that this is the winner, in fact. There is a reason why the rational ones might have more than others. There are reasons for that. But again, we have no idea. It's a fun project. I should mention that, so Trevor Hyde, this was the year he finished his PhD. Recently, together with John Doyle, they've just posted a preprint this year where they found pairs of examples in all degrees that have sort of the winning numbers, the largest known numbers of common preperiodic points. They grow at least as fast as d squared. In fact, there's a better bound than this. This was just to fit on the slide. You can get lots of common preperiodic points for degree d polynomials, and here are some actual numbers for different degrees. So they're very explicit examples, all defined over the field of rational numbers. And they have another story in that paper as well. It's actually very interesting. So I do like this computational aspect of this project, and I think it would be fun to figure out if one can do better. It's 3:20, so I'm going to have to finish up. So let me just mention on this last slides, of course, our silly bound was 10 to the 100. Perhaps M is actually less than or equal to 26, but there's a big gap there. So it would be great to be able to improve some of this. But also, what about in general? Notice this was just for this very special family of quadratic polynomials. We did do some other families, but the computations were very particular to the specific families we were looking at. We conjecture that there are uniform bounds, just as analogous and with overlap with that uniform version of the Manin-Mumford conjecture that I mentioned earlier. We do conjecture that there's a uniform bound over all pairs, not just of polynomials, but of maps, say, on P1, And there should be versions of this in higher dimensions, but some uniform bound on all pairs with a given degree. Unless, of course, they're essentially the same polynomial. The thing that could go wrong is they essentially commute with each other or share an iterate up to some symmetries. So as long as they're not essentially the same, we expect there to be this uniform bound on the number of common points, a very strong version of this rigidity type statement. But I have to finish by mentioning two things. Sorry to go over time a few minutes, but the first is just a few months ago, Mirto Mavraki and Harry Schmidt just posted a preprint where I wrote it in it's a much more general statement than what I've written here. But in simple terms, the idea is if you take any family of pairs parameterized by a curve, so a one parameter family of pairs, and if you assume the family is itself defined over a number field, then they get a uniform bound. And what I want to emphasize is that this uniform bound is not specific to the formulas. It does not use the specific formulas. So it's a much better proof than what we were giving. And the key idea are those preprints, the ideas in those preprints that were just posted last year, especially in the work of Kuhne, his equidistribution theorem, but those were for families of abelian varieties. And so, sorry to skip ahead, but I just wanted to go back. This was the slide I showed you earlier. This was the work that I was mentioning. There's this big story, and I wanted to describe just this piece, which was the small piece about intersections of preperiodic points. But it was really the developments in equidistribution that were posted last year, which allow us to get much stronger results now. And I'm very optimistic about pushing this further and getting the more general statement. And so since I'm done now, I'm just going to leave up the slide that shows what we're really doing, because I didn't say anything about what's actually happening. So I'm just going to leave that slide up and finish here. That's all.
So we don't have online questions, but it's time for questions from the room, if any.
I apologize for that. But in the beginning, when you described this analogy between the Mordell-Weil conjecture and this analytic counterpart, it brings to my mind another known analogy that there is between somehow rational points and hyperbolicity in the other side. Hyperbolicity. Like I'm thinking about the Lang conjecture in the arithmetic, and I think it's called Kobayashi conjecture in the hyperbolic side. So I was just wondering whether there are some, since there are these analogies, where there are also some applications of those techniques in the case of hyperbolicity. In that case, I think it would be rather partial differential equation and not dynamical system, but maybe these techniques can be useful as well.
Yes, so my only answer is I'm certainly familiar, yes, with a number of those questions and results on that side, and how they imply various statements. If you assume, for example, Lang's conjecture, we don't have a whole lot of use for it yet, but there certainly are results. Yeah, so those particular conjectures, I've not seen them employed for more general dynamical results, but there are a number of interesting dynamical results assuming ABC conjecture and generalizations and stuff related to, say, Voitis conjecture and on the arithmetic side, but not so much on the geometric side. So I don't know offhand of any ways to tie that in directly, but I also haven't thought about it. No.
Thank you. Some more questions? Should we?
Maybe you mentioned it, but I'm not sure. So it's a question about your result from 2011, your present an idea of the proof. But what about the proof of Chinese mathematicians? Is the idea the same?
Oh, so the Yuan and Zhang's proof. So it's similar in the sense that they are also working over the Berkovich space. They are also, so there's a parallel story to equidistribution, which is doing what's called a certain arithmetic Hodge index result, but in fact it's very closely related to equidistribution, so many parts are the same. The key place where it differs, and I'll mention, which is actually very interesting and what allowed them to do a more general result, if I could go back to it just to point out, there was one point at the end. When we pass from number, so the number field case is the same. When we pass to working over C, or more generally, working really over a finitely generated field over Q, this is where it's different. And they build this beautiful and very powerful structure to study Berkovich spaces over finitely generated fields in a more general setting and certain height functions, such as in the work of Moriwaki, if you're familiar with it. And so their machinery for this last part is different. So we work also with Berkovich spaces over function fields, which is an example, we can think of it as a finitely generated field over Q, but the techniques are a bit different at the end. And they have this very strong arithmetic Hodge index theorem that they're using, which we do not use, which can be used for more powerful results at the end of the day. So theirs continues to, I mean, they never published, I should mention, they never published their work, but this year or last year, they reposted it to the archive with some stronger theorems, which was actually really nice.
Thank you.
Yeah.
Maybe there is time for another quick question, if any.
I think Claire Voisin has a question. Here.
Yeah, just regarding these equidistribution results, is there anything known sort of about the fluctuations there? So, for example, if you take a smaller subset which has measure epsilon, or so according to that uniform measure, according to which it's going to be distributed, and then you take the first m guys, right? On average, there will be about epsilon m of them in that set, but there might be more, there might be less. And so, for example, if you break your whole space into chunks of size epsilon, most of them are going to be close to having epsilon m points, but some of them will have more, some of them will have less. And is there anything that's sort of known about these kind of distributions?
In general, I think not. In general, I think not. The strength of these theorems is they're in some sense very soft equidistribution results, but allowing you to treat a large class of distributions, in other words, a large class of height functions. So I never defined what I meant by height function, but fundamentally the input, at least on P1, this is the simplest setting, is really just a family of measures. As long as you have continuous potentials, you can run this machinery. So you don't need a lot of special things about the measures. And so as a consequence, the equidistribution result is somehow very soft. You just know if the height tends to 0, your points equidistribute, and there isn't a whole lot you can say. The quantitative versions, though, do take into account, if you know the modulus of continuity or Helder exponents for your potentials, then you can get stronger statements. But the exact answer to your question probably is not known.
So maybe you mentioned it, but in the Kuhne result, this uniform Mumford theorem, he says that there is a bound which depends only on G. Is it explicit? I mean, is there an explicit function of G?
He does not give an explicit bound on that depending on the genus, no. So we don't yet know how it grows with G or what exactly these numbers should be. And one of the sticking points is exactly in this, as I called it, soft equidistribution, is how to control that input and what kind of numbers you get. So it's all depending on certain height estimates, and what the constants are in those height estimates are not so explicit. So at this stage, I don't think we know what the numbers are.
Okay, so I'm told we have to conclude here. There will be time to interact with the speakers also during the breaks. But first of all, I think we should thank Laura again for her beautiful talk.
we continue our program, and now I call Franco Cardin to chair the next speaker of today. Franco.
It is a pleasure to introduce the lecture by Professor Luca Dell'Aglio of the University of Calabria. He is a great and fine expert in history of mathematics. Among many valuable his publications, I like to recall a beautiful 50-page paper on the history of the covariant derivative. In my opinion, it's a beautiful and very essential for any differential geometry. Let me also recall his important contributions on the Treccani Encyclopedia around the scientific and mathematical pages, and also a very interesting little re-edition of the lezioni sulle superfici di Ricci, well commented. Now his tale will be around the golden age of the mathematics in Padua in the 19th century. Please.
Okay. Thank you. First of all, I would like to thank the organizer of this conference for the kind invitation to speak on this very special occasion. In effect, the coincidence of such two important events concerning the history of the University of Padua and the Italian Mathematical Union is closely related to the subject of this talk, which actually concerns one of the most important cases in the development of Italian post-Unitarian mathematics, which is, on the other hand, specifically related to the scientific context of Padua. More in detail, the subject of this talk regards the origin of the absolute differential calculus, and which, as is well known and in a very schematic way, took place starting from the second part of the 19th century, having its most famous systematic exposition in 1901, and prior to its application to physics in general relativity. In this talk, I would like to focus on certain historiographical problems associated with the consideration of the early developments of this theory, and which at the same time highlight the central role played by the scientific context of Padua between the late 19th century and the beginning of the 20th century. The first question concerns the origins of the theory, which, as is well known, are strictly related to the research of Gregorio Ricci Curbastro. In fact, the clarification of this point makes it possible to emphasize the role played by Italian scientific community and by the University of Padua in particular. The second historiographical problem concerns the developments of the theory before its use in general relativity. This problem is also linked to the question of the reception of the theory, a historical process which also presents some problematic aspects, as mainly testified by the case of the Premio Reale per la Matematica of the Accademia dei Lincei. Once again, the scientific contest of Padova played a role of primary importance, above all besides the works of Ricci Curbastro, essentially for those of his pupil, Tullio Levi-Civita. The third historiographical problem concerns the links between the absolute differential calculus and applications. Before its use in general relativity, in effect, the usual image of the absolute differential calculus as a theory detached from application in its early phases of development and then recognized as extremely useful in physics as an image that can be considered somewhat in a form stereotyped that does not totally correspond with its really initial aspects. I would first like to recall briefly what is the situation of the main mathematical teachings held in Padua in the post-unification theory. One of the major mathematical traditions in Padova in the 19th century concerns geometry, above all with Giusto Bellavitis. Bellavitis taught a course in descriptive geometry, which after his death in 1880 was then held by Giuseppe Veronese. At the same time, courses of infinitesimal analysis were held, among others, by Francesco Flores d'Arcais, while the courses of complementary algebra in the early years of the post-Unitarian period was taught by Giovanni Garbieri. Then we must not overlook the important tradition of mechanics in Padova, which was taught in these years, first by Domenico Turazza and then by Ernesto Padova. It is in this context that at the beginning of the 80s, Gregorio Ricci Curbastro began to teach in Padova. At the end of his scientific background, that mainly took place in Pisa at the Scuola Normale Superiore, essentially as a pupil of Ulisse Dini and above all Enrico Betti. In 1877-78, there is a period of specialization in Munich, where he followed the courses of Felix Klein. After being assistant to Dini in Pisa, Ricci Curbastro, at the end of 1880, began to teach mathematical physics at the University of Padova, a course that he would hold for his entire teaching career. Here we see the list of his early scientific production. A brief look of this paper, at the first papers, shows how they generally consider subject of a physico-mathematical nature, in particular electromagnetism, as a consequence of the influence of Betti. Therefore, not surprisingly, Ricci Curbastro began to teach mathematical physics at the University of Padua, as mentioned before. As shown by the other papers in the list, toward the middle of the 80s, Ricci Curbastro's scientific activity shows a clear change of direction, which regards the theory of differential invariance that will lead a few years later to the introduction of the basic notion of the absolute differential calculus, those of covariant differentiation and tensor. In particular, papers after 1882 concerns the subjects of quadratic differential forms and differential parameters. This fact is closely related to the first historiographical problem. That is, to what extent is it possible to say that the theory was really born in Padua, thanks to Ricci-Curbastro research? This question becomes more explicit when we consider different possible meanings of the birth of the theory in terms of appearance of the basic notion and techniques of the theory from an algorithmic point of view, to explicit introduction of the basic notions of the theory with their properties, free publication of expositions of the theory in a systematic form. Now, as is well known, the first point, point 1, does not concern Italian mathematics alone, but various aspects of mathematical thought, especially German, during the second half of the 19th century. The main example is given by Elvin Bruno Christoffel. Here he is the central passage of the demonstration of Christoffel regarding the reduction of the problem of equivalence of quadratic differential forms to the theory of algebraic invariance. In this demonstration, Christoffel, from a differential form G mu of coefficients I1, I2, I mu, with this law of transformation, obtains a new differential form G mu plus 1 of these coefficients, where the symbols in the second part are Christoffel symbols of the second kind. This is the first occurrence of the technique of covariant differentiation. Now, the passage from this phase of an algorithmic nature to the explicit definition of the notion of covariant derivation regards Ricci-Curbastro's work, starting from the study of differential parameters, reprising the technique of Christoffel in a functional way. This is the way in which covariant differentiation appears in Ricci-Curbastro's work as a technique. In this case, the problem is the search of differential parameters, and the paper by Ricci-Curbastro is based on a reduction of this search to the theory of algebraic invariance, similar to Christoffel's work. In the first part, Ricci-Curbastro consider the laws of transformation of the coefficients ARS of the fundamental form, their derivatives, and for Christoffel symbols of the first kind. In this language, XRP is the derivative of the function of XR. On this basis, Ricci-Curbastro obtained the last expression, XHRS, where the CRS are the coefficients of the form reciprocal to the fundamental one. Now, in order to examine differential parameters, Ricci-Curbastro took into consideration an arbitrary function, u, and the laws of transformation for its derivatives, UR, UH, and UHK. And then introduce the function UR in the following form. And using the expression 1 and the expression 2 becomes now the law of transformation of the UAK, in which UAK is expressed in the following manner. This is the first expression in Ricci-Curbastro's work of different covariant differentiation. And here, therefore, we have a use of algebraic invariance because Ricci-Curbastro affirms if one constructs the system of absolute algebraic invariance common to the form phi and to the other forms having for coefficients respectively URS, WRS, WRS, all formed like the URS, with the coefficients of the arbitrary functions U, V, W, this yields differential parameters of the second order with any number of arbitrary functions. Here, therefore, we have a function use of Christopher's technique of covariant derivation, but in relation to the study of differential parameters. This is this thematic shift which can be considered at the basis of Ricci-Curbastro's explicit introduction of the notion of covariant differentiation. This introduction appeared in a very schematic way in a paper in 1887 on the basis of a quotation from the central part of Christopher's theorem. The first quotation, if the expression U, R1, R2, Rp are the coefficients with P indices of a form which is covariant with respect to phi squared, the U, R1, R2, Rp plus 1 given by this expression are the coefficients with plus P plus 1 indices of a form which is also covariant with respect to phi squared. And then the definition of covariant differentiation. If U is any function of x1, x2, xn, the derivative are the coefficients of a linear covariant form with respect to phi squared. By means of the theorem demonstrated above, we can then construct successively expressions with 2, 3, P indices such that those with P indices are the coefficients of forms covariant with respect to phi squared and include the derivatives of U up to the order P. We shall call them covariant derivatives of order P in the manifold, which is defined by the expression phi squared of the square of its element, line element. The central point of the question is that this extension of the idea of derivative is linked, is possible to link to another specific tradition of research in the 19th century, related to the study of differential parameters. This tradition had its origin in Gabriel Lamè's works on the equation of mathematical physics, and then a significant development in Italy with Eugenio Beltrami research. In particular, an embryonic form of generalization of the usual notion of derivation had actually already been present in Lamé with regard of differential parameter of the second order. En résumé, lorsqu'une classe de phénomènes physiques dépend des variations d'une certaine fonction de points, c'est presque uniquement par son paramètre différentiel du second ordre que cette fonction intervient, comme si ces paramètres étaient une dérivée naturelle, plus essentielle, plus simple et en même temps plus complète que toutes les dérivées partielles choisies plus ou moins arbitrairement que n'ont l'habitude de considérer. On the other hand, in his work on differential parameters, Beltrami expanded Lamé ideas of a possible extension of the usual derivation by considering also the differential parameter of the first order. The point of the question is that this extension of the idea of derivative is present in an explicit form in Ricci-Curbastro's work, but now in relation to Christopher's algorithms. This is clear from this quotation. When the line element as the form sum the xr squared, they coincide with the derivatives of u of the order m. And it is possible to consider them rather than differential parameters, perhaps, as Lamé said, of the latter, as something plus essentiel, plus simple, et en même temps plus complète que toutes les dérivées partielles. In this way, here there is another similar quotation. This interpretation, this consideration justify the following general process from the algorithmic phase of the notion of covariant differentiation in Christopher's work to the explicit definition in Ricci-Curbastro's work. At the top of the slide, we have the connection between the studies by Ricci-Curbastro, by Christopher Ricci-Curbastro, using the theory of algebraic invariance. But the definition of explicit definition of covariant derivation is an effect of the intervention of the other tradition of research, linked to the studies of equation of mathematical physics in 19th century. It should be noted that the initial definition of covariant derivation by Ricci-Curbastro refers only to the fact of applying the derivation to single function. This explains the reason for the fact that the explicit definition of the notion of tensor took place in Ricci-Curbastro's work later on. In particular, the notion of tensor was explicitly introduced by Ricci-Curbastro in 1888. In this form, I will denote an mth system as covariant or contravariant to a quadratic differential form phi if it is transformed as a system formed by all the coefficients of a form of order m that is covariant or contravariant to phi. And this is this corresponds to the classical definition of tensor. It is in this specific sense that the introduction of the basic notion of the absolute differential calculus can be referred to Ricci-Curbastro and precisely in relation to his early years at the University of Padua. What we have seen concerns the role of Ricci-Curbastro in the appearance of these basic notions. But Ricci-Curbastro's work also plays a fundamental role with regard the question of the formation of an overall identity of the theory. With the publication of various first systematic exposition of the theory of the absolute differential calculus, the first exposition in Italy in 1888, and the second one, the first exposition at an international level, published in 1892 in the Bulletin des Sciences Mathématiques. The structure of these papers is quite similar, with the first part of a theoretical nature and the second part concerning applications of the theory. Here is the index of the second paper. Then the first part of theoretical paper is followed by the other part, in particular, the last section. In the last section, various applications to physical subjects are present, in particular to the equations, regarding the equations of the theory of elasticity. It is important to highlight that in this context, a systematical introduction of the principle of tensor algebra is explicitly present, considering the tensor operation, somme produit système composé, et the system reciproque. Therefore, it can be said that the absolute differential calculus actually appears as an autonomous theory, essentially in some works of Ricci-Curbastros between 1886 and 1892. And that, therefore, in this sense, the theory actually has its origin in Padua in these years. Let's now come to the second historiographical problem. That is the question of the developments of the theory prior to its use in general relativity. The role of the University of Padua in this context is again of a central importance for several different reasons. First, this concerns the subsequent works by Ricci-Curbastro, which deal mainly with tensor treatments of some topics of geometrical nature, differential geometry, in the sense the study of surfaces, and some points of Riemannian geometry. Some papers concerning surface theory were then included in the publication De lezioni sulla teoria delle superfici. A new edition of this book was published in 2019 in the edition of the Unione Matematica Italiana. From a didactic point of view, it is also important to remember the lezioni sulla teoria matematica dell'elasticità, published after Ricci-Curbastro's death in the second volume of his works, and written in this period. But in these years, another crucial factor in the development of the absolute differential calculus played a central role, related to the contribution of other mathematicians, and above all, Tullio Levi-Civita. In this regard, it is necessary to briefly recall his scientific background, which was mainly acquired at the University of Padua as a pupil of Ricci-Curbastro and also of Veronese. And after a period of specialization in Bologna, Levi-Civita began to teach rational mechanics at the University of Padua in 1896. Here, again, is a list of some of Levi-Civita's early contribution to the absolute differential calculus, starting from his thesis. As we can see, the basic feature of these papers was the resolution of various questions of an analytical and physico-mathematical nature, particularly in the fields of theoretical mechanics and potential theory. For these reasons, in the process of application of tensor analysis before its use in general relativity, a central role was played by Levi-Civita, exactly in this sense. At the end of this period of applications of the absolute differential calculus, during the final decade of the 19th century, there was the publication of a new systematic exposition, les méthodes de calcul différentiel absolu et leurs applications, the best known presentation of the theory. The paper used a few years later by Einstein, and clearly related to Klein's interest for the absolute differential, because the paper was published in the Mathematicianale. This is the structure of the first part of this paper, with an introduction of the theory and of the theory of congruences, la géométrie intrinsèque, and a second part devoted entirely to the applications. Applications regarding the invariant, the differential invariance, applications of nature or geometrical nature, and also of a physico-mathematical nature concerning mechanical and physical application. It's possible to say that excluding particular papers, also important, this paper marks a sort of limit in the development of the theory before its use in general relativity, in virtue of the way in which the absolute differential calculus was considered above all in Italy in this period, which also have some effects on the role played by the scientific community of Padova. As is well known, this question of the reception of the absolute differential calculus in Italy is mainly related to the history, as already said, of the premi reali per la matematica of the Accademia dei Lincei, in relation to various editions of this prize, which was never assigned to Ricci Curbastro. In the edition in 1887, with this commission, the evaluation of the commission was of a substantial expectation, as is possible to read, and not a critical evaluation of tensor methods. As is well known, the situation tends to change in relation to the edition in 1901 of the Premio Reale per la Matematica, which presents some critical statements on Ricci Curbastro's methods. In this case, the commission was composed of Ulisse Dini, Valentino Cerruti, Luigi Bianchi, Enrico Dovidio, Giuseppe Veronese, and the papers presented by Ricci Curbastro were essentially his main works on geometry after 1892. In this case, the consideration on Ricci Curbastro's methods are more detailed and systematic. These considerations are in part positive in relation to the fundamental concepts of the theory, the first quotation. Then the most essential tool of the new calculus consists of a special method of derivation in relation to the fundamental quadratic form, the covariant and contravariant derivation. The covariant derivation was introduced explicitly by Christoffel, and it is Ricci's main merit of having recognized the importance of this fundamental concept and built upon it the new algorithms. But the evaluation of the commission appeared very critical in relation, above all, the application, in particular in relation to the book on surface theory. On the whole, it's possible to read, on the whole, this book by Ricci appears to be worthy of prize for the unity of method that it gives to the exposition of the theory. On the other hand, it seems that the excessive preponderance given to the algorithmic part often leaves the essential geometric content in the shadow, and sometimes leads to enunciating as special results of the calculus properties geometrically evident. The final statement is very famous, but it is important to read. The algorithms he developed and perfection with constant study certainly prove useful, so not indispensable in dealing with various mathematical issues. And of these, we find evidence in the same works of Ricci and in those of few of his followers. But all things considered, in the works presented by Ricci, the really new results do not appear of such importance as to merit the high distinction. It can be said that in this case, the evaluation of Ricci Curbastro's methods is not totally critical, but is critical in relation to the application, above all in the case of application in three-dimensional cases. Partial confirmation of this consideration is given by the question of the identities of Bianchi. In fact, these identities, according to a note of a paper of Ricci Curbastro, were already known to him, to Ricci Curbastro, who communicated them to Ernesto Padova towards the end of the 80s, in the 19th century. They are contained without a demonstration in a note of this paper of Padova, Ernesto Padova. It was then Bianchi in a note, in a famous note in 1902, who demonstrated them, making a reference but without making an explicit use of Ricci Curbastro's methods. Then the difficulties found by the absolute differential calculus in terms of reception led to some historical consequences. First, a partial interruption of studies on the absolute differential calculus in the years after 1901, as testified in particular by the research of Velevicivita, which in these years in Padova tends to focus mainly on various aspects of classical mechanics. Second, what emerges is a consequent image of the beginnings and early developments of the theory, which is mainly related to the studies carried out in the scientific context of Padova. This fact is also supported by certain subsequent events in the years immediately following the adoption of the absolute differential calculus in the relativistic field. This concerned the particular role played by Levi-Civita in the period of the formulation of the field equations and immediately thereafter. It should be remembered that Levi-Civita contributed to this process of events with the famous correspondence with Einstein in the spring of 1915, and which helped Einstein to arrive at the field's equation in November 1915. And then also on the basis of these events for Levi-Civita's introduction of the concept of parallel transport in his famous paper in 1917, written when in the following years, in the following years, as is known, Levi-Civita became also the main spokesman of theories of relativity in Italy, with various papers in this field, and also the author of this. In conclusion, I would like only to mention the third problem to which I referred at the beginning of this talk, concerning the usual image of the absolute differential calculus as a theory abstract in nature, which only later was found useful in physics. As observed from its first developments, essentially for being related to the scientific tradition of Lamé, the absolute differential calculus is connected with various kinds of application in mathematical physics, a process which tended to expand later in the final decade of the 19th century, as already said. And then to appear in the method, one interesting thing to note is that in this paper it is possible to find not only this kind these kinds of application, as already seen, but also a definite general scheme of application of tensor methods. This, in particular, this topic was carried out in a section of the paper with a significant title, Caractères invariants des équations que l'on rencontre en calcul différentiel absolu. It's possible to read. Les équations qui définissent la loi de transformation des systèmes covariants nous disent qu'un système covariant quelconque est ou n'est pas identiquement nul, indépendamment du choix de variables. C'est bien cette propriété que l'on traduit en disant qu'un système tel que a un caractère invariantif ou absolu. Lorsqu'on se pose ex novo un certain problème, il suffit de supposer ces éléments déterminatif exprimé en variable tout à fait générale et de substituer la dérivation covariance selon une forme fondamentale presque toujours indiquée par la nature de la question à la dérivation ordinaire pour que les équations du problème se présentent sans aucun effort sous forme invariantive. Then, in conclusion, it can be said that on the one hand, the absolute differential calculus actually has its origin in Padova as an autonomous theory in the years between 1886 and 1892, specifically in relation to point 2 and point 3, which can be seen to characterize the birth of the theory. On the other hand, even the initial developments of the theory took place mainly in the scientific context of Padova in general, in particular until 1901, because of the problems of reception emerged. And then also, immediately after, its use in general relativity as shown by the contribution of Levi-Civita after the appearance of general relativity. It is therefore in this sense that it is possible to affirm that the scientific context of Padova has a role of absolute centrality for the historical development of the absolute differential calculus at various levels and in different phases of development. Thank you very much.
Thank you very much. We have a little late, but just a question. And then I have a little thing. Has been truly essential, in your opinion, the 1 year staying in Munich of Richie Curbastro, guest of Klein and von Brill, in order to build subsequently, eventually, his absolute differential calculus.
Okay, see, this is a question in general of the influence of Klein on the genesis of absolute differential calculus. It's possible, certainly there is a convergence on Ricci Curbastro of various directions of the developments of the concept of invariance in 19th century. One of these naturally regards Klein, but also the theory of algebraic invariance, the theory of geometrical invariance, differential parameters, and then it's possible to say that on Ricci Curbastros there is a convergence of various directions concerning, above all, this one concerning Klein. Okay.
Thank you very much. We thank again.
Okay, before going to the coffee break, let me call Davide Bariballi, who is going to present the play of this evening.
Hello everybody, so this is just a small advertisement for the tonight play about Levi Civita. So you can see the title, Spaghetti and Levi Civita is the title of the play of tonight at 9 p.m. in Sala dei Giganti. It is in Piazza Capitaniato, 5 minutes walk from here, so you can walk there. And please remember your mask and your badge if you are here as a member of the conference, and if you have invited people, since you're coming from the math department, then your invited will be on the list that is provided by the math department. So the play will be in Italian, and I think that's all, and we can go to the coffee break maybe.
Okay, if you please take a seat,
Ehi, ciao, come stai?
Uno, due.
Quello accanto, sì.
Hai il problema? Ok. Okay, so welcome back. Now we resume with the roundtable on the usefulness of useless thinking. And let me first start calling Prorettore Fabio Zwiner, who is going to greetings.
Good afternoon and welcome to the participants to the roundtable and in presence and remotely on behalf of our rector Daniele Mapelli. The theme of this roundtable is particularly dear to my heart, and indeed I have the privilege of meeting 3 of the 4 panelists in institutions to which I've been linked in my professional career, and that certainly have great consideration for the concepts expressed in the famous essay by Abraham Flexner, and these institutions were UC Berkeley, ICTP, and the ERC. So I'm eager to hear what the discussion this afternoon, and I wish you all a very productive discussion. Thank you.
Thank you, Fabio. And now I give the word to the chair of this roundtable, Telmo Chievani, who is a delegate from the university to popularization of science and communication. And I take the opportunity to thank him very much for the support that he's giving us in promoting the events of this week, also for the beautiful editorial today on Bolive. And thank you, Telmo. Please.
Thank you to you, and thank you to all, and welcome. Good afternoon, and welcome to this roundtable, which has, as you have seen, a very paradoxical title. So, the usefulness of useless knowledge. Maybe you remember very well that this is a quotation of a very famous paper published by Abraham Flexner, so the founder of the Institute of Advanced Studies in Princeton. A very old paper published in 1939 before the Second World War, but it's a paper that is still really in our minds, and it's very, very important also for what we mean by research and basic research today. It reminds me also another very important quotation from Vannevar Bush in the United States, that he was the engineer that led the growth of the United States in terms of research and technology. And I remember that Vannevar Bush wrote many times that the most important innovation came from remote and unexpected sources. So they came from unexpected lines of research, not expected. So that's the point. So we are going to discuss about the importance of research focused on deep questions, so curiosity driven, of course. So basic research, qualitative research, able to produce innovation, but that innovation that is unpredictable, so unexpected. So we decided to share with our speakers today some questions, general questions, and we decided that each of them will answer in a first round some of them. The first one is, why does it happen so often that basic research resulting from curiosity to know, apparently useless, leads to very relevant applications? Maybe it's the first very more theoretical question. Another one is more historical. Over the past 50 years, we have seen an acceleration in applications of mathematical research, and you are discussing exactly in different sessions about that. Why is mathematical knowledge so fruitful and effective? And then again, how important are interdisciplinary and intersectorial network and collective works in mathematical fields today? What are the best research policies, public and private, to promote creativity, innovation that lie at the heart of apparently useless basic research? So the policies for the future. And why do companies ask from mathematicians today, and what works and what doesn't work in this partnership between private and public? So big questions. I propose that we can start with Jean-Pierre Bourguignon, Professor Jean-Pierre Bourguignon. In this case, it's very useless to present him, of course, to you, because it's a great French mathematician, and you know, he was the president of the European Mathematical Society, of the Institute of des Hautes Études Scientifiques à Paris, and of course, president of ERC, European Research Council, from 2014 and 2019. So please, we would like to start with you about your opinions and idea about these big questions. And thanks for being here.
Thank you very much for the presentation, also for the invitation in this extraordinary occasion and extraordinary location. Well, I think to start with, why does it happen so often that indeed useless knowledge is actually pertinent to become useful? I think maybe the first thing is about knowledge. Because to formulate knowledge, one needs to really come up with the right concept. And actually, the elaboration of concept is a very slow process. And when you look at the way it happens, usually it's absolutely, a concept becomes mostly relevant, not where it is expected to be relevant. And actually, I lectured this afternoon for another conference, so still in this building, on spinners. And spinners appeared for the first time ever in the hands of a mathematician, a French mathematician, because he was doing a systematic classification. And he found in this classification everything he expected, except something completely unexpected. And of course, since he was doing his job, he just listed. But then later on, as you know, spinners have become absolute critical building blocks of the understanding of physics. But of course, it was not his motivation, and the way it happened, he was just doing his job professionally. And so this is one example where clearly you can think since he was looking at a topic which was clearly identified, but then all of a sudden comes up something you don't expect. And he couldn't do much with it, but he did his job. And so that was a typical example of useless knowledge, except it was professionalism, being able to identify there was something special. So I think it's in general something which I want to stress, that typically for journalists, but also for the public, concepts are something which are basically God-given. There is no intervention of men. When we do, it's exactly wrong. If you look at energy, for example, which is so central today in everyday life, the concept of energy took centuries to be built, and with a lot of mistakes, a lot of dead hands. So it's only through this kind of totally open search that actually you can come up with the relevant things. And my final example, which I want to give, because it's again more or less considered already forgotten. If you look at how the most efficient vaccines have been developed during the pandemic, it was just because people kind of stubbornly look at how the RNA is functioning, how it can be brought to cells, and many people thought it was just a hopeless effort. But in the end, it's what saved millions and billions of people. So I think that's another example where useless knowledge, which is the functioning of mRNA, was turned through the wiseness, cleverness, and also a lot of investment, because then when you go to the next stage, then you have to mobilize millions, if not more. And therefore, you see, but it looks like this is considered normal. It's absolutely not normal. It's an absolute miracle that this could happen. And this miracle was possible only because people have been stubbornly looking into this, pursuing it in various directions and so on, for the understanding.
Yes, that's great. In philosophy of science, we use this term serendipity. So in the case in which you are searching for something, you have a research question, and during the pathway, you discover something completely unexpected. In the case of mRNA, you can also appreciate this process that we have in science of tinkering. So sometimes we use something already existing for a completely different purpose, for a new purpose, like in the case of vaccine, mRNA vaccine. So thank you for this first moment. Now, I think that we should have connected another very important guest for our roundtable. The technicians say yes. Okay, welcome Ingrid. Ingrid Obeschi, welcome to this roundtable. Ingrid is a wonderful mathematician, a distinguished professor of mathematics and electrical and computer engineering at the Duke University, and the New York Times Magazine defining her as the mother of digital images. And she also working in a wonderful project about the colors of the Scroveni chapel. So thank you for being with us, and the same questions are for your interpretation now. Please.
Well, I think I agree in large part with what Jean-Pierre Bourguignon said, but I also have the take that, yes, it's a miracle, but on the other hand, it's something that we always do. It's a very human thing. Understanding is something that we feel we get when we recognize similarities between different instances that we encounter. So we say, oh, that is really the same thing as that what's going on there. Or this thing that I managed to use in this circumstance, I can also use here. And we've done that over and over again. I mean, people did that in the most elementary discoveries. I mean, making fabrics, sewing, all these were the result of putting together many observations and then using them out of the box or out of context for something new. So it's something that's we like doing and we're good at doing. It's a very human thing. And to some extent, even animals do it because they are studied. They have been noted to use tools. So, and it's exhilarating when that happens. So that is, I think, what we experience when we do mathematics. Mathematics is almost the science of doing this, of observing patterns, systematics in one setting, extracting them and naming them so that we have already a framework with which makes it easier to then apply it elsewhere. So to me, mathematics is the science of defining things in such a way that you can use them easily elsewhere. Those patterns, those logical connections, those structures. So in that sense, I don't find the unusual effectiveness of mathematics so surprising. I think mathematics is essentially that, the fact that we do that.
Yes, and Ingrid, I have another question for you. Which kind of mind do we need in order to detect these patterns? So, and which kind of mind we should educate in order to have more possibility to discover these patterns?
Well, I think, I don't know that you need one particular kind of mind. I think we all have this to some extent, because most people have something that they become very good at and that they're better at. It might be their hobby, it might be something in relation to their work, it might be a special talent that their family knows of. Oh, when we need this, we have to ask Uncle Fred. And I believe that that is because in that pursuit, they saw connections, they saw links that other people did not discern. So I think we should just cultivate a sense of curiosity, a sense of making connections. And there are many, many different ways in which people can do that. And that's one reason why it is so important to encourage many different ways of thinking and many people from many backgrounds, and to cross-fertilize all the time between different people from different backgrounds, people from different cultures, people from different streams of thinking, and have them work together, which was another of your later questions, that collaborations are so important.
And Ingrid, in the early stages of your career, did you have some expectation that later you will discover wavelets, so mathematical functions related to the elaboration of information and digital signals, or it was completely outside your expectations?
Well, of course, I didn't have that expectation, but that's not the only time. I mean, at some point, I was in a system where we were asked to make a 5-year projection of what the research would be doing, what we would be doing in the next 5 years. And I always found this very, very strange, because when I looked back, I felt I could predict maybe 1 year ahead. But 5 years ahead, there was nothing I did that I could have been foreseeing to do 5 years earlier. Now, I realize that not everybody works that way. Some people do work on long-scale programs that they have several different milestones, and they do know which milestones are several years ahead, and that works too. That's not the way I worked, but I knew that when I was working in mathematical physics and I was learning many beautiful properties of Fourier transforms and how they interplay with many aspects of analysis and physics, I knew that those tools were also useful in signal analysis, and I was interested in exploring those and inverse problems. And I wanted to learn about those. And because I wanted to learn about those, and then I had a background that was different from the engineers who were working on that, I saw things in a different way. And so I had different answers to some questions of interest to them. And those answers were then interesting to them. And that's exactly what's at work in this serendipity. But it was because I came from this quantum mechanics background that I thought of things in a different, I thought of time and frequency as a whole, not as something, as two fields between which you make transitions all the time. And that was extremely useful.
And thank you. And here in Padua, we are celebrating our 800 years of history, and we, of course, decided to use as our keywords freedom of research, but also the universality of language of science. And mathematics is the most universal and crossing language in science. But you decided to apply in a very concrete way these ideas in your project for the mathematics, for an inclusive mathematics for example, poor countries and not just for the West. So why it's so important to make mathematics as a universal language for everyone with the same opportunities?
Well, we believe, and we have ample evidence, that mathematical talent can emerge anywhere. And people who find a special joy at doing mathematics and from developing countries can be of enormous service to their countries, while at the same time indulging their passion. And I believe it is important to provide a framework where young people of this type can develop their talent and passion. And now that we have great communications between worldwide, it is possible for them to be in contact with the scientific enterprise, which is global, and not be isolated, and remain or spend most of their time in their own country, where they are rooted in their society, in their family, and so on. And they have all those wonderful support structures that are cultural and that we all thrive with in our own cultures and our own families, but at the same time helping educate a next cohort of young curious minds, which will help their country and develop their science and their engineering, and help the country achieve, in one hopes, a sustainable way, a higher standard of living for everybody. So I believe it is very important to help those young people and to help them help others. So making it possible for them to inspire whole cohorts and raise the level of education in the country and raise the economic level in that country. There have been economists who studied the relationship between a good education in mathematics that is widely accessible and the economic progress in the country. And I was convinced by those studies, and that helped me in my resolve in trying to help developing countries become achieve this higher level. And mathematics is a very cheap way of doing it. I mean, much cheaper than in many of the hard sciences where you would need big labs. And mathematics, because it is so much built on insights and connections, is something that then can relate to many other of the scientific endeavors in that country.
Yeah, that's wonderful. When we talk about science and democracy and justice, this is exactly the point. Thank you. We will come back to you very soon in the roundtable. Thank you, Ingrid. And now with Professor Alberto San Giovanni Vincentelli, we come exactly we have the Silicon Valley here in Padua with you. He covers the Edgar and Harold Butner Chair at the Institute of Electrical Engineering and Computer Sciences at the University of California in Berkeley. And so it's also up to you now to have your interpretation from your expertise about these general topics. And thank you. You don't have, maybe you have, yeah, behind you.
All right. So first of all, I am an engineer. Okay, so don't shoot me, but I'm an and so connected.
No one is perfect.
No, of course. But I spent 1 year in the mathematical division of T.J. Watson Research Center in 1980, so a few years ago, just a few years ago. But why? Well, because my path in engineering has always been paying attention at the fundamentals. So any of my 100+ PhD students over the years, I've been forced to do a minor in mathematics, but not mathematics for engineer, real mathematics. So in the department of mathematics, and a few of my students actually won the prize for the best thesis in mathematics, though it was about engineering. Because engineering has its mathematical aspect. And why is so important to have mathematics in engineering? Because I'm sick and tired of the heuristic method that most of engineers unfortunately use, especially in the United States. And I would like very much to be able to prove that certain algorithms or methods achieve what they are supposed to do. And interestingly enough, I started in again, before 1980, working in numerical analysis, and I did something called the dynamic iteration. I call them waveform relaxation, but that is a way of solving differential equations. Then I went into non-differentiable, non-linear optimization, so things that you don't connect necessarily to engineering. But lo and behold, when I went to IBM, all of a sudden I kind of saw that some of the things that I was studying, because I was interested in this topic, could be applied to what? To design, design of integrated circuit. And so it happened that because we were able to demonstrate the convergence of some algorithm, the optimality of other algorithms, the industry became interested because they could see that there was value in what we were trying to do, and they pushed us to form companies. Okay, so in 1983 we formed a company called Cadence Design System, still alive in NASDAQ, and it's about $50 billion as market evaluation in NASDAQ. And then in 1987 we formed yet another company, all based on Boolean algebra and the like. And also that had success, is $60 billion on the NASDAQ market. So, mathematics in the end, even though it's used by an engineer, does have an impact. And so when we say useless, I would say not yet useful, okay, instead of useless, because useless is a negative connotation. But the point is that whatever you do that has some foundation, fundamental aspect, is going to be useful one way or another. Wait 100 years, 200 years, 300 years, doesn't matter. It's not yet useful. It will be useful. And in terms of a meta concept, instead of a concept as Françoise was referring to, the meta concept in mathematics is the capability of formulating a problem and demonstrating that the solution that you try to apply to the formulation of the problem has certain properties. Now, the fact that you do mathematics gives you that machinery that is able to do the deed, right? So that you can indeed have an impact in your work. Now, by the way, when we were talking about, you were talking about Vannevar Bush, but there is something that you guys forget, because Vannevar Bush had what was called the Pasteur quadrant, right? And I'm sure you know, but the Pasteur quadrant has two axes. One is fundamental understanding, which you can apply to research driven by curiosity, right? The other axis, though, is consideration of use. And so Vannevar placed people in the various quadrants to represent what he meant. And so the fundamental understanding with no consideration of use, he put Niels Bohr, that, as we all know, is a physicist with deep mathematical understanding, also in quantum mechanics and the like. And then on the no search for fundamental understanding was Thomas Alva Edison, who was completely ignorant, right? He just was doing things and then hoping that it will work, right? And then up here was Pasteur, that was the combination of the two. Now, if you want to look at the research that is done in the United States, no matter in which field, is always kind of characterized this way. So is fundamental understanding, otherwise there is no substance, but is also what could it be used for? So when we talk about, uselessness, is uselessness in the sense that if I can solve this problem, maybe I can have the following fundamental impact on things. Now, as an example of this that is very enlightening, at least to me, is the work done by my colleague Jennifer Doudna and Michel Charpentier on CRISPR-Cas9. Jennifer was doing work to try to understand why bacteria were resistant to viruses. And she found out that there was a mechanism that would allow the bacteria to cut the DNA of the virus to disable it, right? And then from there, it came up CRISPR-Cas9, that is a method to edit precisely our genes, right? And so she won together with Michel, the Nobel Award last year or 2 years ago, I forget. But this has become the source of many companies that have been formed in the United States, some in Silicon Valley, some in the Harvard kind of environment, right? And so that was as abstract of a research in biology as you can imagine, but that in less than 10 years had a fundamental impact also on companies and ways of curing diseases, not only mRNA, but this also is, has a potential of eliminating all genetic disease, all of them, right? Because you could go in and eliminate the disease gene and replace it with a good one. Of course, you can imagine all kinds of other uses, and I don't want to get into that, because another important point when we talk about research and impact on society is the ethical aspect, and we always have to keep this in mind, right? There are some fundamental research, I mean, think about, of course, of nuclear physicists that had an impact on the creation of course, of the atomic bomb, but these new technologies like biology and so on do have fundamental ethical impact that are as important as what we have seen in the past years about the nuclear engineering and the like. Now, in terms of the, again, of mathematics, but I would say physics as well, I don't think that what we are doing now in Italy is wise, right? I'm talking about Italy because France is better, much better from this point of view. It's the fact of driving the university towards application of what is intended to be application. And so I believe that there are several diseases in the universities right now. One is I call patentitis. The other one is H-indexitis, right? And what does that mean? That you want to measure H-index. You cannot measure the impact of research. I have a colleague of mine who won the Turing Award. You know what the H-index he had? 5. Why? Because he published 5 papers. But they were so fundamental that he got the Turing Award. Now, in Italy, he would not have gotten a chair. No way that it could be promoted. H-index of 5, right? So that's bad, right? Anything that measures exactly something that cannot be measured, which is the impact and the deep depth of research, is very negative. The other one, patentitis, means anything you do in the university, you got to patent. And then you look at these patents, and they have no value whatsoever. Nobody wants these patents. And so what is the value of that? Just because you can put, I have 20 patents? Okay, as I said, we formed 2 companies. The sum of the 2 is more than 100 billion. You know how many patents I got? 2. Why? Because I was forced to patent 2. Because I don't believe in patents. Patents is something that you use to defend yourself, not to safeguard your research. The most important thing is to move fast. Is speed, not patents, what matters. And the speed with which you bring your fundamental contribution to be of relevance in industry. Again, this is an engineer who speaks, right? So the quickness which you move from the concept, right? We were talking about concept before. From concept to actual use of that concept is what matters, is what makes a difference in terms of the innovation in the industrial world. Last but not least, unfortunately, I'm surrounded by people who do useless research. My 2 sons, one is a philosopher, he's professor at King's College, and the other one is doing mathematics at Princeton, right? So where the book that you quoted, Flexner, was the director who took Einstein into Princeton. But there is a book that just came out 3 years ago from Princeton. The other author was Deercraft, who he was, until a couple of years ago, the director of the Institute of Advanced. And why did he come out? Because we had Trump, my dear friends. And Trump was a disease that you wouldn't believe in the entire scientific community. It is the negation of science, right? So we have to defend, we have to build antibodies for the fundamentals and for the role of research, not only in industry, but in society. It's a very important fact that people be used to reason in scientific terms, which is, of course, the capability of replicating what you say that could be done, so that everybody could check your facts, and the rigorous derivation of what you do. Okay.
Thank you so much. Donald Trump is a negation of also many other things other than science. I was exactly thinking to the same example of the gene editing and biology. That's great. What is also amazing in this case is the disproportion between the initial investment in this research on the immune system of bacteria against viruses and what you see today in terms of companies both quoted in Wall Street and so on. I have a short question that is a curiosity related to the economic side, so then we can come to Paola. That is, Alberto, you are consultant for many big companies, right? Intel, Kawasaki, Sony, IBM, Chrysler, BMW, and so on. We know stories in the past of great companies in funding basic research department with slow research, so no rapidly application needed. Is still true today? That, is it possible also today that you have in United States companies funding basic research in a slow and without the expectation of application in the private sector?
Yeah, well, I hope that there is no economist in the room, but one of the things, if you look at what was possible, right? If you look at the companies that did this kind of research, you can count them on your fingertips, right? Bell Labs, IBM, TJ Watson Research Center, and I know it very well. Xerox PARC, the Palo Alto Research Center, and a few others. I'm not so familiar with the medical companies, but this is it, right? Now, look at when this research was funded, when these companies were de facto monopolists, okay? So they had so much power in the market that they had to pay back to society something, right? And of course, what is better than giving back by fostering long-term research, right? So it was an excuse, if you like, for their power in the market. So if you want to have good research, industrial research, you got to have monopolies. Otherwise, there is no way in which companies are going to divert their funding to fundamental research, because there is the stock market, and the stock market looks at the bottom line, right? And so if you are a monopolist, the bottom line is great no matter what. But if you are not a monopolist, and if you look at the present companies that do some reasonable research, long-term research, reasonable, not super excellent, but reasonable, is Microsoft, Google, and to some extent also Facebook, right? So, well, guess what? In their domains, they are almost monopolists. Guess what, right? History repeats itself over and over again. So if you're looking for companies to finance at interesting rate so that you can have some return, you have to look at monopolies.
So we have just two possibilities: great monopolists or public funds. Right. Okay.
Well, I mean, it depends. I'm talking about long-term, research, as you pointed out. If you look at shorter-term research, then of course anybody can do it, as long as the margins are good enough. Now, there is a cancer today in the stock market, which is caused by the push by shareholder activists and all of that to repurchase your stock. So if you have great profits, then they force you to buy your own stock, because by doing that, you reduce the number of outstanding stock, so that the value of the stock of the investor goes up, right? But this doesn't create real deep wealth. The wealth is created if you do new products, right? And new products implies innovation and so on. But in order to do that, you need to use the profits that you make to foster your presence in the market. So that is indeed, of anything, is a cancer that we have to watch out. But I don't know, at some point, Hillary Clinton, during her campaign, said that she was going to forbid companies to buy their own stock. That is one thing that you can try, but then you can still, the activist investor will find another way to get to the same point, right? But definitely is a cancer that we need to be worried about.
Thank you. So now we are talking about the economic side of this field. So I give the floor with great pleasure to Paola Corna Pellegrini, CEO of Allianz Partners, with a great career in this field, a mathematician, has training and also strongly involved in policies for gender equality, diversity, and sustainability. So, Paola, the floor is for you. What's your opinion about these challenges, topics?
So, first of all, good morning, everybody, and thank you for inviting me. It's a big challenge for me to speak after all those scientists. I'm not a scientist. I just got my university degree in mathematics 41 years ago. But then through an MBA, I discovered marketing, and therefore my career were all based on, let's say, other experiences, but mathematics and the approach, the methodology, the method, the problem-solving approach, the analytical approach helped me in whole my career. So I have to thank this, and I want to say that for the future generations, because we have now a lack of competencies in not only in digital, generally speaking in STEM, so science, technology, engineering, mathematics, and we as companies have the need to have more people trained and prepared on these subjects. So I want also to give a perspective that these subjects are not only for researchers or for scientists, but are a background, create a background that is really helpful in any career or job you want them to perform. And anyway, I also want to say that we have to look at the purpose and to give a purpose to the students in order to identify how these technical aspects, technical skills can be applied to have a better world in the future. We will come back to that, but application is key. And this is what we professors said before as well. We need to speak about application, and mathematicians should look at the application of all their science in this world. And there are many, many aspects. And I come to some of these aspects that are key in our industry. For example, I worked in many industries. I worked in toiletries, let's say, fast-moving consumer goods, and then in pharmaceutical for 15 years. So what Professor said before resonates to me, and also serendipity. I could also talk about many products that came out from failures and became a big success because we found the way to value the weakness of this, like antibiotic, which were working only in a specific organ, and then this was their strength in the market because they were super safe and not creating addiction. Just to mention one thing that I could leverage in Zambon when I was the CEO of Zambon Pharma. But coming back to the challenges of all the industries now, we are all facing, let's say, opportunities and challenges at the same time. If we are not fast enough to capture the new trends, both in terms of data analytics, data mining, data management, on the one hand, and all the digital transformation of all our companies. In terms of data, data are key. Now there is a say that data is the new oil. And somebody says that this is not true, because if you have too many data, you are paralyzed. And this is also something we have to be scared about. So we need to have data. We have tons of data now. Technology gives us many data, but if we don't organize them in a proper way, we are really paralyzed by the data, or at least we cannot use them to improve our way to do business. If we can organize, collect in a proper way, organize data, store data, and then have from mathematicians the right way to aggregate, to cluster data, to have different, let's say, reporting from the data source we have, then we become more competitive. And competitiveness goes through, for example, is very important for pricing. Above all in the insurance business, pricing is based on data, and more data you have, more data scientists you have, actuarial and from economical standpoint, better you are in pricing, and that means in being at the same time competitive and profitable. Because the key point of insurance is to predict the risk and this frequency and severity of your claims. And you need to have sophisticated mathematic approach to do so. The other point is to profile your consumers or potential customers. And all the companies that were mentioned before are absolutely extraordinarily good in profiling us. We know because as soon as you Google something in the net, in the internet, you then receive a proposal of to buy something or to go for other researches in the internet. But if we use this without being, of course, overwhelmed by that, but being use that as a company, you can offer the best products, the best services to your potential targets. And in terms of digital transformation, for example, to digitalize as much as possible our processes means to be more efficient, to be more productive. And this, at the end, is, of course, drives costs down. And this, at the end, gives the opportunity to decrease prices or to give a better service. And on the other hand, digitalization is a really powerful tool to improve the user experience. Because if I'm a traveler and I have an insurer with Allianz Partners and I have the digital app that allows me to be geolocalized wherever I'm in the world, then when I call, and maybe I cannot call by phone, but I have the data connection, I can give my position, and our people and means that we can send to him or her to solve the problem in the location they found in US or in Vietnam or in China, it's at the best because we can geolocalize and we can meet the person more easily. So this is just to give concrete examples how digitalization can really improve the user experience and safety. And of course, there are many other examples. For example, blockchain can be a powerful tool in terms of claims management in a way that protects insurance companies from frauds, for example. We could immediately refund a person who has lost the flight or who has the flight has been delayed if we are connected directly and we are sure that the information we get is the true one, and we can immediately refund our client, and the client has the money to buy a new ticket, for example. So concrete examples how to apply is the way application of mathematics or digital transformation can really improve. And finally, if we think a future world where we will have smart cities, we will have traffic lights which will be handled by algorithms, by managing the traffic and the flow of the cars. And this will improve our experience, the traffic light, but will also improve the environmental impact, because we can manage at best the usage of the vehicles and decrease pollution. And when we will have autonomous vehicles, for example, here the world will change totally, because we will have sensors in the vehicle, sensors in the highway, in the route, and those will be managed through algorithms that have to, of course, use many data and have to take into account many situations. And of course, ethics will be key, because the algorithm will have to choose if I have to go against a person or against, I don't know, a pillar or something which is anyway same size, maybe, but more dangerous for the car. So this is something that is really where I would encourage mathematicians to focus on, and the scientists to focus on, how to ensure that the world we will live in, that our children will live in, is, of course, automized, is, of course, much more digitalized and easy to use, or democratic somehow in terms of access to data, to information, to knowledge, and to services, but at the same time need to be regulated, because otherwise we are victims and not really, let's say, the beneficiaries of this all new world.
Thank you. That's great. Can you share something more about this question of this point of the algorithm? In the sense that, for me, the algorithm is quite never serendipitous, in the sense that it profiles you, and it proposes to you always something that is surrounding your previous choices. So never surprising, never. So is it possible to build more serendipitous and exploratory algorithms, or is it against the market, or is it against the choices?
To be more scientific?
To be more, because the web is a universe of information, but we have these algorithms that try to channelize our choice, and just so. Is it necessary, or is it just the only possibility we have?
I don't know. I don't have an answer, but for sure, I encourage to try to have a wider perspective. When when mathematicians design algorithms, they look at the history mostly, and that was what is worrying me above all, after certain aspects. First of all, this prevents from innovate somehow, and this is something I leave to the scientists how to overcome. But above all, it replicates the bias that are in the reality and that are in the algorithms, in the data. I give you an example. The algorithm which is behind LinkedIn, everybody I believe knows LinkedIn. We all have, I believe, a profile. Had to face a huge problem because of gender bias, because it was designed by the famous WASP, white man, and I don't think Protestant, but white man for sure. And so for women, for example, CEO, never happen to appear in a statistic, because we are so few that from a statistic standpoint, it's at the 20th paper we could come out. So they had to intervene very quickly to fix that. But it would be much better to avoid that. And to do so, to be honest, there are some changes. I mean, women have to participate in the STEM market, in the STEM education, in the STEM jobs. Because if women are not part of the designing of the future of our world, then they will be always excluded, at least at the beginning, because their perspective will not be considered. But not because men want to exclude women. It's a matter of having the sensitiveness to take into account what relates to women life, women habits, women behaviors. Also in pharmaceuticals, for example, the gender medicine has just started recently. And we have totally different symptoms, for example, or issues related to the same pathology. For a heart attack, thank you. For the heart attack, the symptoms of a woman is many times in the back and not in the front or in the arm. And so also all the digital solutions, application for self-diagnosis didn't take that into account at the beginning. Or there are many drugs that work better on men than women. So the research should be split between men and women with statistically significance in the two targets.
Clear, thank you. So now, moving to the future. Moving to the future challenges. I have a question for Professor Jean-Pierre Bourguignon, a great curiosity that I have. It seems to me that we are facing something paradoxical, because we know that serendipity, basic research are unpredictable, okay? So it means that it's impossible to plan it. It's impossible to have a planning of basic research. So what are the best policies in order to at least promote basic research? So what are the ecological, social conditions that could promote more serendipitous, more creative, and more innovative research, according to your experience?
Well, there are two aspects to that. One, you started to touch upon it, which is policies. And actually, necessarily they are policies, because at some point you have to spend money, either as a state or as a company, and therefore you have to allocate resources, and you need mechanism. And very often, if you look at public money, the people who decide on the money are people from the political world. And for them, at least in democracies, what is important is to be re-elected. So it means that the horizon is well set. It's the next election. And I must say that I fully understand the rule, but we have to go beyond that. Because in particular, a number of the challenges for which science will be inevitable, or the extensive use of science will be inevitable, are challenges which really require a long-term effort, also mobilizing new resources, new capacities, and of course to achieve that cannot be achieved within one mandate of anybody. So we will need let's talk about democratic countries for the moment, that actually we manage to convince that on some issues, the usual policy, at least it's the one which is usually practiced in France, that if a new team comes, the first thing they do is to claim that what the ones have done before is completely wrong. And there could be some wrong things, but I don't believe everything is wrong. So you need to obtain that people agree that there are some things on which, maybe with some slight changes, but there is a long-term acceptance of some objectives. So that's for the policies. And then concerning the policies, and I will touch on the second side in a minute. Concerning the policies, one thing which is extremely important is that you let the people who know the best really make the decision. And I think in terms of science, the people who know the best are the scientists. And therefore, it's extremely important that the policy leave enough room for a bottom-up approach. That is the approach where the scientists, and of course you even have to challenge them so that they are not reproducing too much what they have been doing, that they are really daring to do things. And I must say that our community, the academic community tends to be very conservative. So I think you even have to challenge them so that they accept to take some risks. So concerning the policies, I've been confronted with that quite a bit in my function in Brussels. The fight for bottom-up research is permanent, and depending who is the minister and how the government is organized, you have to repeat to them, it's extremely important to them long-term objectives. That's for the policies. Then the next thing, which I'm very glad you touched it, is people. What makes a difference in the end are people, and both in the public sector and the private sector. And I think the best managers of company are people who know, who value the quality of their staff very much, because that's what makes a difference. And so now the key point is to give to the next generation the prospect that if they are interested, if they have shown some capacity, they will have some possibility of really engage themselves into research or engage themselves into new adventures, and that they are not just saying, oh, nothing is possible, so I just go back to the simplest objective that I can grab, and that's it. You need to get the next generation to dream. You need to get the next generation to be ambitious. And for that, you have to show them that there are possibilities, that there are opportunities. And you have to create these opportunities and to challenge them at the same time. I mean, the young people, one thing which I've seen in France to an extent which really kills me is the fact that, well, people are not succeeding, so just diminish the standards. But that's just absolutely wrong. Young people do sport not just to diminish the standards. They do sport because it's challenging. And they know that if they don't make efforts, they are not going to be successful. So I think, of course, you have to help people, to accompany people in the right way so that they can achieve high standards. But the idea of lowering the standards has never been the solution to solve the problems. You have to be ambitious. And of course, you have to make it possible. So I think this is also another thing which in recent years definitely has not been the policies followed in our countries, exactly to the opposite of China has been doing at an extraordinary extent. The figure I keep repeating, because of course China has been investing huge amounts of money into research. And you know, the budget for basic research in China increases by 7% per year. So I don't know for Italy, but I know for France, we are just very, very, very far from that. I know for Italy it was bad for quite some time, so maybe it's getting better. But the key figure I want to recall is that if you look at the most cited, 1% most cited papers, the China had a 1% share in 2000. Now the share of China is 21%. So it means that not only they have put money, but they have increased the quality tremendously. So that's what makes a difference. And I see this in my field, in mathematics now. A huge proportion of the best young people, they are Chinese. I lectured this afternoon, and about 2/3 of all the papers I quoted were by Chinese mathematicians. And so this is something we have to get used to, but also to recognize that this didn't happen randomly. It was the result of a systematic policy, which of course can be interfered with some other consideration. But still, I think to give the opportunities for young people is absolutely decisive for Europe to be competitive, for example. And for the moment, there are very few countries where this is available. And I think this has to change. And in particular, the pandemic has created a movement among young people saying, wow, I don't see any prospect for my future, then I'll just quit. And I've been actually flooded by messages by people from many different disciplines, from many different countries in Europe, writing to me saying, all my PhD students are leaving. They are not going to go for a postdoc. They feel that there is no future for them, so they do something else. And of course, if they go to a company where many companies want to hire qualified people, then also the salary will be better than if they stay in academia. So if you combine the lack of perspective and the certitude that your salary is going to be not great, then it could turn into a disaster. So I think this has become a very, very important issue. And for the future, as you know, with the very uncertain future we are going to face because of geopolitical reasons, and probably the significant increase in military expenses which will come, I think we really should be worried. So I think concerning the future, we have to look for two things, which is policies and really people. And if we miss one of the two, we're going to miss the whole thing.
Yeah, that's very important. We have, unfortunately, the same worrying data about young people in Italy too. Yes, but the depressive mood that they have after the pandemic. And about China. So, in your view, what is the best strategy that Europe, so that the European Union should implement in order to answer, to reply to this very aggressive strategy from other geopolitical powers?
Well, I think in the case of Europe, you see first of all, one thing which I could witness is the extraordinary diversity of the systems in Europe. And so if you look at it from one angle, you feel this is a handicap. I don't think it is a handicap. I think it can be actually a value that you can cultivate, but you have to do it in the right way. And this requires compatibility between the systems, that you really don't create artificial barriers that you don't even identify and which in the end are the main driver. And also you have to make sure that really the resources go to the people who are going to use it, who will be the most ambitious. That's why for the ERC, for example, that's really one thing we have been telling the panel members, please take risk, look at the most ambitious project, because that's what's going to make a difference in the long term. Of course, there are other ways of funding research, and that's fine. I'm not saying all the money should go to ERC, but first of all, a significant money should go to ERC. And second of all, as a community, we need to look for ambitious things, because you know that's where most likely the breakthroughs will be coming. And you can never be sure the breakthrough will be coming, but you know boundary conditions, as we say in mathematics, which have a good chance of creating this. So I think for Europe, it's first of all to obtain something which has been totally missed by 2020, which is the level of investment finally reaches the 3% of GDP, which was presented as the goal for 2020, which now has been pushed to be the goal for 2030. And I'm not sure it's going to be achieved. For example, France has been totally stagnant at 2.2. And of course, when you count this, you count public and private investment. But it cannot be. I mean, at the same time, you have Israel with 4.2. You have South Korea with 4.2. And you could see for South Korea, for example, the extraordinary transformation of the Korean society. Which was one of the poorest right after the Korean War. Of course, there was an objective reason for being very poor, but which now is one of the most affluent countries in the world, and with an extraordinary progression of the level of qualification. South Korea at the moment is the country which has the largest tertiary education, in particular for women. When, if you look at the history of Korea, that's one of the countries where women were the most repressed. So, I mean, these are examples you have to study, look into, and see how you can achieve that. And for Korea, it was very simple. For 60 years, education was the absolute priority of all governments, including the dictatorships. So, because they had also some bad governments during this time, but they always kept the massive investment into education. Why don't we try that?
Great message. Thank you. Thank you again. And Ingrid, do you have some comments with respect to what we have said so far, and what, again, also for you, what are the future challenges that you see for mathematics for the future?
Sure. And so some comments I had is just past comments in passing. I agree so much with everything that was said. There was the comment about patentitis and indexitis and so on. It's really, in a sense, what happened there is that on the one hand, people who have to make decisions wanted to have ways of measuring progress. And they said, so how can you measure? And I think at first these indices were maybe a useful way to illustrate successes in some cases. And of course, that's all they ever can be, because you can find counterexamples like the H-index of 5 for the Turing Award winner. And in mathematics, we can have many such examples, because many people who do very impactful research don't publish enormous amounts of papers. But it does measure something. The problem is always that it becomes enshrined as the way of measuring, because as soon as something becomes enshrined as that way, people start gaming it, and then it becomes even less useful. And then, but that to me is an illustration of something that is characteristic of human societies. We like to try to find structures and rules and so on, and then to make a rule of this is the way you will decide that. And as soon as you do that, you have lost the game, because things are dynamic. There is never, you cannot think of these problems as solved once and for all, these ways of estimating or evaluating and so on, because your way of estimating it becomes part of the structure, and that changes the game. And so I always think that all these questions, the analogy I use is the bicycle. With a bicycle, you cannot get anywhere if you are not willing to deal with the instabilities of riding a bicycle. To get to move, you need to constantly balance things. You can see that by the fact that if you go with a bicycle in a rigid, in the tram rails, you fall. It's because you have no longer that degree of freedom of moving. So we have to be aware of the fact that, yes, we want to evaluate things, but no, we should not make fixed rules, because they become obsolete very quickly, because they change the system. So that's, but I like this idea of being dynamical. I mean, because it means that the creativity enters again. That's the same thing as how can we get serendipity into these search engines when they give us answer. I never answer anything about, did you like this movie, did you, and so on. I don't want them to have more data than they already have about me. I want to be surprised more than be guided in channels towards certain products. But about the future, I do think education is extremely important. I also do think that it's extremely important that we encourage people to work together and to do unusual things, things that are not quite the patterns of before. And I think people spontaneously will want to do that, because that's our history. We've always wanted to do that. We invented so many things through our cultures and our history and in all different nations on earth. And we will continue to want to do that. It needs to be, some people invent terrible things. So there needs to be some oversight. There needs to be a lot of bottom-up ideas need to be allowed to percolate, but indeed there needs to be some evaluation of what are the most productive directions. But I do hope that we will find ways to do this productively and sustainably. And we have to raise to the challenges that are posed by our present society and in many ways. I mean, the environment, the global warming, also the impact of algorithms on social behaviors. But I'm fundamentally a big optimist. Mathematics has made me optimistic. So I do hope and I think with everybody in your audience and listening to this, that we will work towards finding good ways of making this all filter out.
Thank you so much, Ingrid. Thank you for all the audience here. So I think that some messages are emerging as convergent. So, for example, that big data are not enough, maybe, because we need mathematicians with good questions, right? So Alberto, also for you, the conclusions about the future. So what, in your perspective from California, what are the future challenges that we are facing?
Well, there are so many, but I would like to point out some of the things that have been said about funding and policies. Now, one of the things that I notice is that, again, connecting to people, is that the review process as it is now is flawed. Review for grants, review for papers, review for careers of people. Why is it flawed? Because let's take the example of the Chinese papers that are 20% the most cited papers. Today, just before coming here, we had a meeting of the committee to give the Best Paper Award in IEEE journal, right? And so guess what? The most cited papers were all Chinese. And then I said, okay, let me take a look, which is an important point. Let me take a look. So numbers don't tell the truth. So I look at these papers, and guess what? 90% of the citations were from the Chinese community. Right? 10% only from Europe and United States. When I look at the content of the paper, it's just boiled water, right? And so you have plenty of this paper in the 20% most cited papers, because that's the way the system works also in China. I got, of course, to evaluate professors in China to be promoted. And guess what? They use H-index, and so you game the system. And so you don't favor the real value of the person, you look at numbers, because you have no courage of taking decision. Everybody's trying to push the responsibility to somebody else. ERC, for example. I was a reviewer for ERC, I was a reviewer for European contracts and the like, and guess what? There are so few people of the real scientific community that do that work because it's a pain in the neck, and after you have done it 20 times, you don't want to hear about it anymore. And so who is doing the reviews? Bureaucrats. I mean, there are these companies whose goal is to help people to write proposals and to evaluate the proposals. And what do? They go like a rubber stamp. They look, okay, do they have this statement? Yes, point. They don't have it. 0 point. And then you look at the grants that are funded, they are the ones that have all the box checked. And one case, I really scream my lungs out, because I say, it is impossible. This research proposal is really good. It didn't check 2 boxes. These other proposals are miserable. They check all the boxes, they get funded, this doesn't get funded. Why? That is an important question in terms of policies, right? So how do we ensure quality reviews? Because no one has the courage to say, this is garbage and this is good. And you put your face on it, right? But unfortunately, or fortunately, it depends, peer reviews is secret, right? Who has given this information? So the only way to find out is if you participate to that process, right? So people, also good people, to evaluate reviews, to evaluate proposals and the like. In my opinion, the best model for funding future research, which is important because you need a lot of money to do. Some you don't need that much money, but some you do need money. Think about quantum computers and the like. The DARPA model in the old times was based all on people, again, value of people. So they said, okay, the future is important to interconnect computers, right? So the internet at some point was called ARPANET, and then it became DARPANET, and then it became internet. But at the beginning was all DARPA that was paying for the interconnection of computers. How did that get done? because DARPA had a deep pocket, and they funded the best research group, and they funded University of Illinois, Stanford, Berkeley, MIT, some of the research lab of the government to be connected among themselves so that we could find the way of making it work for everybody. But it goes towards lots of money, targeted money. They didn't give it to University of Cincinnati, they gave it to the big institution. You may say, you replicate again the model of the people who have fame and, you know, and you don't favor the growth of young people. Yes and no. You know, there are also grants that favor the young people, and I would venture to say that instead of reducing the amount of funding, spreading the funding equally among people, what you should do is try to identify the new big researchers along the line. Now, the other thing that I hate about the United States, I must say, is hype. You know, when something comes up and there is some kind of wave coming, right? The tsunami, AI. Isn't that a tsunami? I mean, geez, you cannot get a dime unless you say that you use machine learning to do anything, right? Machine learning to clean your shoes, grant. Machine learning to do the best risotto, grant, right? And you say, well, I would like to study this fundamental issue in mathematics, no grant. Where is machine learning? You don't have machine learning in your proposal, right? So this is horrible because there is all this hype. Every time there is a hype, there is a boom, downturn, then nobody gets any more money, right? And which is a waste, because maybe something there is to save, but there is a counter wave, right? So talking about the algorithm and what the problem is there and the deep question, right? Because it's always this thing about correlation. I mean, people look at data and they try to correlate, right? So if you bought shoes yesterday, I'm going to provide you a list of shoes. The next research you do, you say, I would like to know about quantum computing. And yes, okay, there is this shoes by this. I asked quantum computing, not shoes. Right? And because it's based on what you've done the day before. I mean, this is an extreme case. No, don't believe that that's what happens. But the key point is that you have always to balance the search from the data, because the data, of course, data are important, right? And physics, mathematics, data is important, no question about it. But what you should try to find is causation, and causation you have to think. I mean, what the data tell you are not necessarily the deep truth. So you have to abstract what the data tells you to find the real causation. So when you talk about women and so on, why is that a problem? Because they correlate, you know? They say there are 200,000 men with that heart attack, and they all have it here, right? And, oh, by the way, there are 5 women that have it here, right? 200,000 versus 5, done deal, right? But what is the causation? How does the pain reflect on the body? And then that is the causation. So maybe because the anatomy of a woman is different from the anatomy of a man, you can find where the pain is felt. That is the use of data with intelligence to understand what is the causal relationship, not the correlation, the causal relationship. And that is what I think should be done. And that's where mathematics, of course, has a big role to play, right?
Thank you, very clear. Great, thank you so much. And Paola, so it's up to you to propose to her some challenges for the future. And I also to discuss some detail about the history of Zambon, because I'm curious about, in the case of Zambon antibiotic, who understood that it was a promising serendipity, and what happened in the case of that discovery?
I would start from Zambon case. So there was this research which happened before my arrival in Zambon. So I inherited this product. And then I made it a further success, let's say, leveraging on this uniqueness from a marketing standpoint. But the researchers were the one who discovered that this antibiotic was working also in the vescica, I don't know in English, the vescica. Bladder, thank you, sorry. And not working in the other organs, in the rest of the body. So it was a failure because the antibiotic has to have a broader spectrum. In reality, I don't know exactly who, but among the researchers, I believe together with marketing, said, yes, but if it works only in the bladder, then it means that it's safer. Because one of the key problems of antibiotics is the resistances, which is one of the issues we have in the world now, no? And after COVID even more, because there was an abuse, maybe not needed, of also usage of antibiotics. And having one antibiotic which was specific for cystitis, in that case, made this the big success. And therefore, we launched it focused with a specific positioning, asking the commercial authorization for only this specific indication, which is cystitis in a certain specific case of cystitis. Urinary infection, cistite in Italiano, urinary infection. And therefore, this was a clear case of serendipity. I have another one, which is less, but in Novartis, we used to have a laxative that in reality was a sugar, alternative to sugar in the initial researchers. And then they discovered that it had a laxative effect. So it was not good as a substitute of sugar, but it became a big success for that. So just sorry to speak about these things. When you work in the pharmaceutical world, you ask me this question and I have to answer. But these were two cases that became big successes in a serendipity way. And what I could suggest to mathematicians, I mean, first of all, I am also listening to you in terms of problem of having funds to continue or to have a long-term research above all. I believe that partially, this could be partially helped by partnering with the industry, partnering with companies. In Italy, it's not so well established this, only in certain sectors maybe, but the university and industry generally are not really partnering very often. I had the chance and the luck to meet with some professors of engineering, not mathematics, of La Sapienza University. And I partnered with them. I built an innovation lab at Allianz Partners, Italy. I was the first in our group to create an innovation lab, and I built it with the university, with engineers, and we built together a master in inventive engineering. And the reason why I choose them is because they were already advanced in researches applied to industry, starting from drones, let's say, which were not my case, but which are very much applied also in the insurance business, for example. But in our case, for example, we designed a totally new offer based on new trends on mobility that taking into account the new intermodal, multimodal mobility trends of the people, above all young people, but not only. And therefore, we designed a new offer, totally new offer, based on the coverage of the person and not of the vehicles. And in that case, technology was an enabler, not really the final aim, but was an enabler. Another concept which was really very good, but we couldn't launch because unfortunately I didn't find the funds in my group, was a product, an Internet of Things concept, which was targeted to elderly people living alone. And you could imagine how strong this could have been during COVID, where people were lonely at home, facing also the anxiety of having COVID or even avoiding having COVID. And this was an IoT that was connecting these elderly people to our platform where we could have received their calls, emergency calls, but also give them support for, reminding drugs intake during the day, or putting them in connection with their relatives and so on. So we designed solutions targeted to customers. And the last message that I want to give is, customer, consider not only as a consumer, but as a human being with all their needs, should be the beginning of any researches for the companies. So if mathematicians, engineers want to support the development of the economy, of the industries, they should partner in understanding the customer needs and, if possible, to predict the future needs.
Thank you, Paola. It's time to close. I have to thank so much Fabio and all the colleagues from Mathematician Department, because you gathered a so incredibly high-profile panel. So thank you so much to all our guests. You can thank. Thank you. Another floor for Fabio for future schedule.
Now, I just want myself to thank warmly, and we are really grateful for this wonderful roundtable, and it will be the source of inspiration for all of us. And okay, we see you this evening at 9 p.m. for the play that was explained by Davide Barilari, Spaghetti and Levicivita. See you this evening. Bye.